Hey, what is going on? We are here for the APEC conference, and I am going to start up the stream now. Gonna add everybody here. Say hi, everyone. We are live on YouTube. We're just gonna. I want everyone to share this link around. We have trouble getting. People aren't getting notifications on my streams and stuff. I don't know if there's someone playing with the algorithms that doesn't want people to find this info or what, but please share this link around on social media. I'm going to go and post it on Twitter and a couple other sites now, and I encourage you all to do the same, and we'll try and see if we can't get a bigger audience to turn out and give us some criticisms, man. I love inviting more people from the mainstream scientific community on to and get more physicists on to know that this is going on. So I've been posting it around on social media groups, on physics pages and stuff, to encourage more people from the physics community to check out what we're doing. And Tim, why don't you tell us what's going on today for today's conference? And
Oh yeah. Well, and actually, so we have Amar Vakil and John Clymer are going to be talking about quantum gravity and a really extensive model that they've been working on, and they're doing a lot of computer modeling to back that up. But first, we have, and actually he just joined us, Mr. Roger Shoyer. And Roger, thank you so much. It is a true honor to have you present for us. So Roger's nervous about his bandwidth, so we're going to play that. We're going to play his presentation as a video, and then just do a live Q&A with him, and that way we don't lose anybody if his connection drops. So that's our lineup for today.
yeah, good to be aware of this stuff ahead of time before we run into issues. Starting to learn the ropes of this streaming business, huh?
Well, yeah, it's a lot of new stuff all at once, right? I mean, we've got multi-channel web streaming, and then we've got conferences with sometimes, 60, 65 people in them now. So it's a lot, and it's all kind of new, and the software's got its own set of quirks, but I'm really excited that we're able to do these.
Yeah, this is really great, getting everyone from the community together for a team. Get off this planet and let's build something better than a rocket to get us to space. There has to be better options. There has to be a lot better ideas and engineerable ones. And it's great getting the community together.
Well, and the other thing too is Ron Keat has mentioned some of these. There have been a few big conference events, right? The STAFE conference, I think that was pretty big. There was the MITRE 2003 High Frequency Gravity Wave Conference. There have been a couple others, and then lots of smaller events. But the challenge is, these events, you only get a few folks, right? And it's difficult to share perspectives, and then most of them aren't recorded or documented well. And so the problem is, it helps, but it's still really fragmented. So the nice thing about what we're doing is it's really comprehensive, and then because we put it all up on YouTube, if anybody misses it, they can still capture that. And this, I think, again, Mark Sokol and yourself, you guys kind of came up with this idea. I think Estes Park was the first that kind of pioneered this, right? They were stuck because of COVID, and they said, okay, we're going to do it online this year. We're not going to do a...
Yeah. It was definitely Estes Park, man. When that conference happened live and on Zoom, we just got the idea. It's like we don't have to rent out a hall. We don't have to rent out find a university or a host. We don't have to have people take plane tickets. We can do this all virtually, and that was the start.
Yeah. Well, but the interesting thing about Estes Park was, and they did have some brilliant presentations last summer, but they had their schedule, and they said, okay, we're going to do our conference, we're done, and that's it. And then everybody was like, that's great, we want more. So that's kind of how we got started with this. And in fact, we would like to have we would like to have a lot of the Estes Park presenters on as well. So that's something that we're working on.
Yep. I'm typing in the chat, brought to you by coronavirus and Estes Park. The combination. I guess this, you have to look at the positives.
I'll jump in for a second, if you're okay.
Yeah, no, go for it.
I'm just casually interacting. So you folks are getting the mainstream folks you're getting their engagement at some future point. How's that coming along? Or is that?
Yeah, well, so the first thing that we've done is form kind of a community forum, right? And again, we're meeting about twice a month. We're broadcasting out to, I don't know. I mean, Jeremy has 100,000 person audience. I've got about a 10,000 person audience. Now, in terms of actual views for that, typically it's like 2,500 to 5,000 in the first 2 weeks that it goes up on YouTube. Then we get, again, 60, 65 recently, live and then usually another couple hundred on YouTube live stream. And I promote this in, the advanced propulsion group. So it's going out to a fairly mainstream crowd, as well as a lot of enthusiasts and just, people who've had kind of a deep interest for a long time. So it's a very mixed audience, I think.
That's good.
I also want to get into like more, clipped up, really short clips of highlights of stuff, because I think that would draw more people in for if we had shorter videos, because some of these discussions tend to go on rather long for the casual audience, I would say. The people that are generally tuning into this are the people that are really super interested in the physics and engineering of building stuff. So it's kind of like a select and refined group, which is kind of cool, but it's also needs to there's also work going on to try to get it again to a bigger audience. But we're here and we're doing it, so.
Yeah, and we're getting there over time, and and it's interesting. There's a lot going on in this area right now, and then I think that the public interest, because of stuff like the UAP thing, I think the public interest is also kind of higher than it's been in quite a while. So,
what I'm hoping will happen with it is that if people are out there and see like, oh well, these guys don't have the best ideas, or I could do it better, that they'll join in, rather than completely ignore it or whatever. I hope we can get people that like know that they're like, all right, well I can do this better, and we'll come on and show us, rather than the trolls, like there's some of these people that really like to troll. We've attracted a couple of those people in the group, and I haven't responded to any of that sort of stuff. I've kept out of it, but I have observed it, and I think it's I don't know. I think it's it's not conducive to the truth of what we're trying to do. We're trying to run experiments here, and I'm hoping that eventually, when we get a lot of these experiments more thoroughly conducted, we can get some data, and we can try to publish this in some way, and maybe get it peer reviewed for our results, including our failures. Because those are important too.
Yeah. Well, guys, I'm going to mute myself out for just a moment, and I'll stop my video, and I will be right back.
So let's do a little highlights reel of the American Anti-Gravity show for the conferences of the past, and show some of the cooler ones going back.
Jeremy, are you keeping tabs on the updates on that Alexei Cherkov guy? Who's working on? We have this guy Charlie who's working on the Alexei Cherkov Graviflyer device, and he found somebody on Facebook by the name of Chris Hardiman who was working on it as well, and got 80 grams of weight loss. And then about a month ago, he passed away while working on it from apparently a heart attack. So he might have been killed by the device.
So
we're in talks with it.
Alexei Cherkov. I haven't been following this. No, I didn't keep.
Okay, so Alexei Cherkov has all those. It's basically two plates that are spinning around, and there's a whole bunch of Tesla coils and all different shit.
Yeah.
There's a lot of speculation that it might be faked with a string. because it does look kind of
Or a
iffy,
pole.
but
The other one was a pole. You could just use a really small, stiff metal pole on the ground. And
right. And it was possible to fake it. But somebody reached out to me who is a PhD electrical engineer who's actually replicating this device, and he told me that he's seen other replications that were successful with 80 grams of weight loss. Didn't fly, but 80 grams of weight loss is still pretty freaking impressive. And this guy who got the 80 grams of weight loss just passed away from a heart attack while working on the device. And we're in talks with his widow to get the device, but she just wants to make sure that there's going to be some recognition of her late husband's work.
all right, you can hear. They said my sound was terrible. I don't know. I pushed a button. Hopefully that fixed it. But was my sound coming through for you guys?
Oh, we heard you just fine, yeah.
Yeah. Some people are saying the sound isn't good. Can you hear the guests? Or you know, let's see. People,
Yeah, it's
a couple
good.
people. I'm trying to see if they can hear everyone and refine if the sound levels are okay in the live track. Some people complain and just, I don't know if it's. My stream has an overlay of white noise. Hold up. How about now? I gotta see if my stream's. My sound always sucks. All right, yeah. So, anyways, Alexei Cherkov. So you think it's a fake?
I'm not convinced either way. To me, it looked like it was fake. Tim spoke to him and got a whole bunch of gibberish. I think Wayne Ojala also reached out to Alexei and got a whole bunch of gibberish as well. And but this guy Charlie, who's a PhD electrical engineer, is actually building a device. And there's another dude, Chris Crawford, who passed away while working on this device. Got 80 grams of weight loss, and we're in talks with his widow to get the device from him and any notes that he had. So it's like, it's starting to look a little bit more promising. When people are working on stuff, I'm interested. When people are talking about working on stuff, it's a lot less interesting.
Well, yeah, I'm looking back at the videos. I got those on my screen for the APEC conference, and it goes back to 4 months ago with the Estes Park conference, which is anyone who's new to this, that's probably where you should start diving through. Check out Hal Fern. Yeah, definitely just check out all of them. I would start back at the Estes Park conference and then dive right into all these APEC conferences. And if you're familiar with certain things and you want to learn more about it, we have some of the people that are the really good engineers that dug into it and studied it, and we try to seek out the best experts in the field on this sort of stuff, and we're gonna try to get more experts on in the future, or anyone who wants to come on and present about a certain topic, even if you're not an expert, if you've done some research that you want to share that you think is worthwhile, I guess, but. What do you guys think about the? I'm trying to encourage more and more guests to get on and help us out with these projects and stuff. It's great to hear all the different people that I can't wait for this guest that's coming up. This is going to be super exciting. How much time do we have left before it's 3 p.m. right now? Jesus.
Yeah, we are there. We are there. Well, guys, why don't I do this? Why don't I mute everybody out? And I will count this down, and I have been experimenting with screen share for just the video. So I think that we can get this to work well, fingers crossed. So I'm gonna mute everybody out now. Okay. And I will count this down and we will get started. And I should apologize, I've got more people joining right on the hour, so. In 3, 2, 1, Welcome to APEC. It's April 3rd, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Roger Shoyer will present an in-depth review of the highly publicized EmDrive propulsion technology, and Amar Vakil and John Clymer will drill down on their work on a control system and a lot of computer modeling to enable R&D in topics concerning quantum gravity. After that, we're going to catch up with the latest research from the Falcon space team, and we'll be wrapping up the event with an open discussion and ad hoc presentations. So just a couple of quick reminders. You can view conference replays, details, and speaker information on our website at www.altpropulsion.com. And please help us promote the conference. Please share that around if you're able to. Post that into various groups, send to friends, things along those lines. Please save your questions for after each presenter finishes speaking. We have a Q&A session after they wrap things up. In the case of Mr. Shoyer today, we will be starting with a video. And so we will go to a live Q&A session after that. Please type your questions into chat, and we will go through them after each presenter finishes. So let me introduce you to our first guest. Roger Shoyer is a British chartered electrical engineer with 48 years experience in the space and defense industries. He's the inventor of the EmDrive propulsion technology, and for the last 19 years has been the director of a small R&D company, Satellite Propulsion Research Limited, SPR. Roger's extensive career includes work at CAV Limited, Sperry Gyroscope, and Marconi Space and Defense Systems. And through his work at SPR, the EmDrive has become nearly a household name, being featured in Popular Mechanics, Wired Magazine, Space.com, National Geographic, New Scientist, Forbes, and many more. So without further ado, thank you to Roger for joining us. And what I am going to do is start our video. Okay, so let me share the screen.
I don't have any audio. I'm not getting any audio or sound. I'm trying to unmute myself and tell them everyone else can't hear too. You guys aren't the only one. Everyone's blowing up the chat right now on here. So
Okay, guys, let me try it. Oops.
oh great. Well, more stuff for the cutting room floor. This is why we do it live and cut it up later. Dr. Disrespect. What? Jeez, these trolls. The Matrix has us, guys. I'm sorry for the, I'm sorry. I don't hear nothing either, so I'm really sorry for the, audio. Video's working, but the audio is not there. People cannot hear. I still can't hear either.
Tim, you could try playing it on your speakers and just put your microphone next to the speaker.
Okay, that's what you've done in the past? Okay.
Yeah, that's pretty much what I've done. So change the, just like put your microphone over there.
Yeah, I will try that. Guys, and if the sound quality is too bad, let me know. Let me know.
You should have given me a
Okay,
copy.
so I'm going to bring this back up. And again, my apologies. I had thought that it would share audio as well as video, but okay, let me try this one more time.
Hello, everybody. Talking today in Drive.
We're good.
I'll go through the theory, engineering, and the applications. Now, the technical reports and the papers, conference papers that are referred to throughout the talk, you can download from our website, EmDrive.com. I'll take questions after the talk, but if you want to email me the questions, you can do so at the address shown. So what is EmDrive? Well, it's a new propulsion technology, which is a propellantless technology, not reactionless, but propellantless. It works by propagating a traveling electromagnetic wave inside a tapered section of waveguide, which is the cavity. It's resonant, so the wave travels backwards and forwards. At the large end of the cavity, it approaches the speed of light, and at the small end, it's much less than 1/10 the speed of light. So the force at the big end is large and the force at the small end is small. Now this difference in forces causes a resultant force, which we call thrust, in one direction, which you can see shown by the arrow, and according to Newton's laws, of course, it provides an acceleration in the opposite direction. Now, one of the things that you'll hear about is that thrust can be very large for superconducting cavities. So where did EmDrive come from? Well, it goes right back to 1974 when Professor Eric Laithwaite suggested that gyroscopes could provide a means of reactionless propulsion. This was his 1974 Royal Institution lecture. Now, at the time, the UK nuclear warhead program called Cheveline was suffering from propulsion problems, and in this very gyroscope, the company I worked for, were under contract from UK MOD at Fort Halstead, Kent, on the Cheveline program, and in January 1975, we're tasked to look at unconventional solutions to the propulsion problem. Well, I was part of the team that looked at this, and I went back to a paper by Professor Alex Cullen of UCL, a 1951 paper, and this was key to the solution that I proposed. It was an electromagnetic solution rather than the mechanical solution that everybody else was trying to do. I sent the report into Fort Halstead, and then in November of that year I was sent to Sperry headquarters of Long Island, and also down to their research site at Clearwater in Florida. And we discussed all sorts of microwave technologies, fairly advanced technologies. Then in October 1976, Professor Roger Jennison of Kent University published the first of a series of papers on aspects of electromagnetic momentum, and he carried on through to 1989, publishing these papers. Meanwhile, I had gone back to my day job in both the defence and later in the space industries, and it really wasn't until the 1990s that the concept was resurrected, and it was run as a parallel program to Project Green Glow, which you've already heard about, and it became EmDrive. So let's get down to some basic theory. And first of all, we need to look at radiation pressure, which is the process which produces the force. Now, first of all, it is not pressure. If you look at the equation, F equals 2p over c, you can see that it is in fact a force, not a pressure. And Cullen showed that this equation can be derived from the basic electrical machine equation, F equals BLI, which all electrical engineers know, where B is the magnetic flux density, L is the conductor length, and I is the induced current. Now, this is the basic equation for all electrical machines. You can also derive the radiation pressure from combining Newton's F equals ma and Einstein's E equals mc squared. So the whole basis of EmDrive is classic physics, which has been around for hundreds of years. Cullen also showed that the force on the end plate in a cavity is modified from 2p over c by multiplying by vg over c, where vg is the group velocity. Now, he showed this both mathematically and experimentally. And so in a tapered cavity, if you have two end plates with VG1 at one end and VG2 at the other end, then clearly the resultant force produced by the cavity is F1 minus F2, which is shown by that basic equation. Now, Dr. Bailey, who was actually a former pupil of Cullen, but was then working at the Royal Radar Establishment at Malvern, showed that this radiation pressure can be greatly increased by use of a resonant cavity. And this again, he showed both experimentally and theoretically in 1955. So when you have a resonant cavity, you have a resonant frequency, and therefore you can change the thrust equation in terms of wavelengths. Lambda naught is the free space wavelength, and lambda g is the wavelength at the different velocities. And you can also then measure the resultant force from one transition of the electromagnetic wave to approximately Q times the transitions, where Q is defined as the stored energy in the cavity divided by the energy lost per cycle. So let me iterate that EmDrive is based on classic physics, which has been understood and accepted for many years. So EmDrive does not work like this. It is not the electromagnetic wave pushing against the end plate like a passenger pushing against the windscreen of a car. This is obviously wrong because any such force will be opposed by a reaction force R. And it stems from this wrong idea that photons are billiard balls bouncing off a wall. They are not. You have to treat them as electromagnetic waves, and you have to look at it a little more deeply than this rather naive construction. So EmDrive is an electrical machine. However, unlike a normal machine where the conductor is moving, in the case of EmDrive, it is the magnetic field that moves. So for the incident wave, the moving magnetic field H induces a current I in the direction of the E field, which you can see by the arrows in the diagram. Now this produces a force F, which opposes the movement M of the conductor relative to the field. Standard electric motor idea. It's based on Lenz's law, which goes way back. And you can see that when the wave is reflected, the E field is in fact reversed. And this is similar to the back EMF, which is created in an electric motor. But the really important thing to take from this slide is that it is the conductor itself, which is the end plate, which pushes rather than being pushed by the electromagnetic wave. And this was clearly put by a Chinese professor, Professor Yang Yuan, who said that EmDrive is in fact a black box pushing against the rest of the world, just like us. So we now have to look at what happens in the cavity with this unbalance of forces at each end. And really the only way to solve this is to do a momentum balance. And there you start off with the wave being propagated in the middle of the cavity, where obviously at propagation the two wave momentums in the opposite directions must cancel out. Therefore, ρ1 plus ρ2 equals naught. And if you look at the momentum at each end plate, you can see that the total momentum lost at the two end plates works out at 1.6 rho. Therefore, the momentum gained by the waveguide itself must also be minus 1.6 rho. What we're just showing with this very simple balance is that EmDrive obeys conservation of momentum. One of the early objections to the EmDrive theory was that the sidewalls, the forces in the sidewalls would counteract the end wall forces. Now, and indeed this is true for just a standing wave. But you have to understand that the standing wave is a result of a large number of traveling waves. So if you look at the effect of the wave forces, you'll see that for surfaces which are at right angles to the wave motion, you will get a maximum force. But for surfaces that are parallel to the wave motion, you will get zero force. So clearly, the idea is to correctly shape the cavity, and what's shown here are spherical end plates, such that the end plate forces are a maximum and the sidewall forces are zero. So we can look at this with a very simple mathematical model, and you'll see in the diagram we show both spherical end plates and flat end plates. Now for the flat end plate, you will have an axial length of LA, but you'll have a slant length of LS. And if you look at what the path length error will be, the total path length error, then it is obviously LS minus LA. But for a resonant cavity, it will be Q times LS minus LA. And this very rapidly leads to a wavefront phase error, such that this phase error becomes indeed greater than half a wavelength very quickly. And this clearly will spread the bandwidth, reduce the Q, and will indeed introduce sidewall forces. You can see the what we call the mean path error effect on the flight thruster characteristic, where to obtain a Q of 55,000, which is what we obtained, you need to keep your mean path length error down to 0.1 of a millimeter. It requires pretty accurate machining. What it does mean is that if you build a cavity with flat end plates, it really is a waste of time. You'll get zero thrust out of a flat end plate cavity. The other important law that EmDrive must comply with is the conservation of energy. And if you look at the diagram, you can see that microwave energy is inputted into the cavity. It is stored in the cavity for a short period of time. And if you allow the cavity to accelerate freely with continuous energy going in, some of the stored energy is then converted into the kinetic energy of the cavity. The rest of the input energy is continually lost as heat. Now, the important point about this illustration is that when the cavity accelerates, the stored energy will decrease because some of it is turned into kinetic energy, and therefore the thrust will decrease. And this is a lovely example of EmDrive obeying the law of conservation of energy. You don't get something out of it for nothing. Now, conservation of energy leads to a very interesting situation when there is no mechanical load on the thruster. If you look at the chart, you can see that in the first few microseconds after switch on, the stored energy, which is the blue line, increases according to an exponential function, whereas the kinetic energy increases according to a square function. So if the kinetic energy increases faster than stored energy, then I'm afraid the stored energy cannot build up, and the resulting thrust, which is shown as the green line, will just simply be a short pulse. Now, this is important because when you're in orbit, where there is normally no mechanical load force present, you do need to adopt loading techniques to start up. Now, the inertial loading of the spacecraft itself occurs once the acceleration is established. So, if you only have inertial loading, you must also take into account what happens when the kinetic energy gained by the spacecraft becomes greater than the stored energy. And what you then need to do is to pulse this device. And so energy conservation is important because it dictates pulse operation when there is no other loading other than inertial loading. Now, for a typical simple first generation thruster, these pulse lengths can be a few seconds with the interpulse periods, as you can see from the graph, measured in microseconds. So effectively, you have almost a continuous thrust, but with just a small ripple. So now we get to a more complex part of the theory when we look at the effect of Einstein's special relativity. Remember that we have a cavity that has electromagnetic waves moving at relativistic velocities inside the cavity. So inside the cavity, Einstein's rules apply, whereas outside the cavity, Newton's rules apply. And the thing is that inside the cavity, the velocity of the electromagnetic wave is completely independent of the velocity of the cavity itself. So VG is totally dependent on the dimensions of the cavity and has nothing to do with the velocity of the cavity itself. Indeed, if you're an observer measuring the velocity of the wave, you will measure it as Vg. You will not measure it as Vg plus Vc. This would take you above the speed of light, which is impossible. Now, to cope with this, what we do is we add a term S0 into the thrust equation, which actually is a term that uses Einstein's equation, the addition of relativistic velocities. The other point about this is that because the Vg is completely independent of Vc, the wave and the cavity form an open system. Also, although it's a closed cavity, as a system, it is open and it allows momentum to be transferred between the wave and the cavity. However, during the acceleration of the cavity, you'll get a Doppler shift in the traveling electromagnetic wave. This is simply because at each end of the cavity, the guide velocity is different. So you'll get a total Doppler shift in the traveling wave. This only really causes any problems when you have very high Q cavities, really when you're into superconducting cavities. But if you look at a simple mathematical model behind it, shown in the diagram on the left, you will find that you can calculate Doppler shifts for both an acceleration, a positive acceleration, and a negative acceleration, or a deceleration. So as you accelerate the cavity, you get a frequency decrease and hence an energy loss. So it acts, in fact, like an electric motor. If you use the cavity to provide a braking action, so you get a deceleration, it gives you a frequency increase and thus an energy increase, and the device is simply acting as a generator. So how does this affect a typical thruster? If you look at the characteristic on the far right, this is a superconducting cavity using liquid hydrogen cooling. And you can see as you accelerate, as the cavity acceleration increases along the horizontal axis, so an uncompensated thruster will lose its specific thrust fairly quickly. But there are methods of compensating, and this means that you can improve the characteristics such that you can get sort of reasonable accelerations of up to 1G is possible. Well, we've looked at the theory of EmDrive, and now we'll look at the challenges of the engineering of one of these devices. And as with all engineering projects, you start off with a design, and if you are going to correctly design the microwave cavity, you have to solve the guide wavelength and wave impedance equations. These equations are well established. You can go to any microwave textbook. And what we've done is used a spreadsheet tool to solve these equations along the full axial length of the cavity using increments down to, say, 0.1 of a millimeter. And This has proved very successful for the last 20 years. We've predicted performances for different cavity shapes, sizes, using different modes. So, and each time we've got a very accurate prediction compared to the measured data. You can use a finite element software package to give you a picture of the E and H field structures, but you must remember that this is for a standing wave only, and it can give you an inaccurate picture when it's actually measured as a real cavity. This slide shows the design results for a T113 CubeSat cavity. And you can see in the left-hand graph that the wavelength increases dramatically as you approach the small end at 140 millimeters, whereas the impedance drops off, heading rapidly towards zero. I mean, this is effectively demonstrating that the electromagnetic wave guide velocity is approaching zero as you approach the cutoff dimensions. If you look at the right-hand characteristic, you can see that we're able to plot both the E and the H field as phase plots. And this is important when you decide where you're going to place the input loop, which you can see in the blue dotted line is placed at a maximum H field. And where you're going to place the detector probe, which is an essential part of the cavity, where the red dotted line shows it's placed at an E field maximum. One of the most important processes which you must go through when creating a successful EmDrive cavity is to go through the tuning process that is necessary to ensure that the loaded Q that you actually measure comprises of the unloaded Q of the cavity and also the Q of the input circuit. And you can see from the equation that if the input Q is equal to the unloaded Q, then you will maximize the loaded Q. So it's important that the input circuit, whether it's a loop or a probe or a slot, must be tunable, and it must be tuned to the match the cavity impedance at the input position and also at the resonant frequency F0. Now this causes quite a problem because the thermal response of the cavity and the input circuit are significantly different when you start putting real power into these cavities. And what this means is that the cavity tuning itself must be digitally controlled from feedback from a detector probe and the reflected power at the input. In practice, what you can do is you can vary the input frequency to cope with the variation of the impedances and the resonant frequencies of both the loop and the cavity. Now, when you're setting up a cavity, when you're doing the tuning, it is most important that you use the detector probe in a two-port measurement system. Many groups have tried to tune cavities by simply looking at the input power and return reflected power at a single port, the input, and what they do is they end up with a beautifully tuned loop. You know, it matches the 50 ohm source, both in frequency. It gives an apparent very large Q, and indeed very large return losses. But what you're actually doing is you're simply tuning and setting up the loop with no coupling into the cavity itself. It's quite easy to do this, and it's deceptively easy, in fact. So if you're going to get power into the cavity as opposed to simply dissipating it in the loop, you need to use the detector in a two-port measurement system. And this is actually vitally important because many organizations have failed in their attempts to produce the thrust out of a microwave cavity because all they're doing is simply putting the power into the input loop. A good way of checking for this is to actually measure the temperatures across the cavity. And what you should do is you should see that the main thermal emission is at the large end plate. If you find that the temperature around the input connector shoots up, whereas the two end, well, particularly the large end plate stays reasonably cool, you know you've got a problem. That you're not actually putting any input power into the cavity. So we have talked about the problem of the Doppler shift you get when you accelerate a high Q cavity. And in 2014, we worked out how to compensate for this in what we call our third generation cavity. Now, the basis of this is that the axial length of the cavity is slightly increased using piezoelectric elements as the acceleration causes the Doppler shift to reduce the actual resonant frequency of the cavity. Now, the one important aspect of this is that the waveform is now a circular polarization, because as any radar engineer will tell you, this enables you to easily detect the difference between the incident wave and the reflected wave, and this enables real-time control of the frequency and the axial length during each wave transition. Now, obviously, you can't keep extending the axial length of the cavity indefinitely, and this leads to the requirement for two cavities. And you can see on the right hand graph the effect of the increasing thrust in one cavity being counteracted by the decreasing thrust in the other cavity. These are exponential characteristics which follow the stored energy characteristics in each cavity. But the actual output is effectively a constant thrust with a small ripple. So now we'll turn to the development of EmDrive, and again, an essential part of any engineering project. And this took place in the UK from about 2001 through to, well, it continues to this day, but the bulk of it was done during 2001 to 2010. were funded by the UK government and a bit of private investment. We were monitored technically by DSTL, that's the Defence Science and Technology Laboratory at Farnborough, where the main guy was a chap that some of you may have come across, David Fern. He was known as the father of UK electric propulsion. He's unfortunately passed away now, but he was a very good technical monitor. He insisted, for instance, that we were able to identify and calibrate out all the spurious forces that might affect the measurements we were making. We started in 2003 with the experimental thruster. This was a low Q, about 6,000, and we were getting about 19 millinewtons per kilowatt. It was driven by a standard commercial magnetron, which, as you probably understand, is bolstered, so it's amplitude modulated. In 2006, we moved on to a demonstrator engine. Q was increased by about a factor of 10, so we were at this point getting 243 millinewtons per kilowatt. As a mean over many experimental programs with this particular engine. It was a complete engine. One of the things we did was actually to put it on to a rotating test rig, and videos of that are actually available on our website. This actually was the key to encouraging the American defense organizations to get interested into EmDrive. We moved on by effectively splitting our work between a flight thruster, which we finished in 2010. This technology was actually transferred to America under what's called a TAA, a Technical Assistance Agreement. This was all set up by the State Department and the UK Ministry of Defence. In parallel with the flight thruster, we worked on our very first superconducting thruster, an experimental thruster. Very difficult technology, but great fun to work with. Now, one of the things that I should mention is there is a big difference between the early two thrusters, which were using magnetrons, which tend to be fairly wide band, and therefore do not require such extreme manufacturing tolerances, but once you move to narrowband inputs from a signal generator and powered through as an amplifier, you need to move to very precise control over your dimensions and alignment. So here we have a couple of views of some of our test rigs. On the left, you can see if you look very carefully, you can see the flight thruster set up on a static thrust measurement apparatus. This actually is a composite balance arrangement that's fully described in the test report available on our website now. It's finally been released for publication in the public domain. On the right, you can see a demonstrator engine actually mounted on a dynamic test rig. This rotates on an air bearing. The whole rotating assembly weighs about 100 kilograms, and the idea was to demonstrate that EmDrive will indeed accelerate 100 kilogram spacecraft in orbit. If you look carefully at the videos, you'll see that the test rig rotates in an anti-clockwise direction. In the photograph, you can see you're looking actually at the large end plate. So it is accelerating in a direction, large end plate to small end plate. And one of the beauties of this particular set of tests was it demonstrated absolutely that EmDrive obeys Newton's laws. And indeed, the accelerations that we measured on the test rig, they were quite the same in terms of thrust as was measured on the static thrust measurement. So in effect, we were demonstrating F equals ma, which was very satisfying. So because EmDrive obeys Newton's laws, you must think about this when you're actually testing a thruster to measure thrust. And the thing you can't do is simply take an EmDrive thruster, put it on a set of scales, turn on the power, and expect the weight to change. You know, that just is not going to happen, and it's fairly easy to see why. If you look at the left-hand diagram, you can see clearly that if the thruster doesn't move on the balance, then the thrust will be compensated by a reaction force, and of course you will measure no change in the balance reading. You will measure no weight change, and really you shouldn't. Now, one of the things about this setup is that you can use it to calibrate out all the noise on your measurement system. And this was a very powerful method of establishing what the spurious forces were, and what their causes were, and how we calibrated them out to satisfy our Ministry of Defence technical monitor. If you want to think about it as an analogy with a conventional rocket, it is simply like putting a conventional rocket engine on a balance, and again the thrust from the rocket, which conventionally is points upwards, is compensated by the exhaust pressing down, if you like, on the balance pan itself, and again you'll see no weight change. All straightforward Newton's laws, but the thing to remember is that if the thruster is loaded with a mass which is greater than the thrust, you will simply not be able to measure thrust on a simple balance. So one of the things that has to be done if you're going to satisfy serious peer review or indeed technical monitoring is you have to be able to model mathematically whatever your test assembly is. And this is particularly important when you're trying to work with very low preloads on your thruster. If, for instance, you do a numerical model of this simple ideal beam balance, and then calculate what's going to happen over the first few microseconds after you switch on the thruster, you will see that, for instance, in the middle graph, that as you increase the preload from about 2 micrograms to 500 micrograms, the kinetic energy delivered to the thrust apparatus drops remarkably down. And this, of course, enables the stored energy to rise following a natural exponential curve. If you reduce the the 500 microgram preload down to as low as 2 micrograms, then of course the kinetic energy shoots up and in fact closely follows the stored energy characteristic. So there's only a tiny amount of thrust left, and you can see in the right hand graph for a 2 microgram preload, you get a very tiny, an almost unnoticeable pulse of thrust. And this is what happens if you don't add some preload to your thruster. And this is particularly important if you're going to test your thruster on a very high resolution balance arrangement. Ironically, the better the resolution of your test equipment, then the more of a problem you have with requiring a preload. So while we were doing our development work in the UK, there was work going on in China, Russia, and America. In 2006, a UK magazine called New Scientist published a cover page article actually on EmDrive, and this caused a bit of a controversy. In fact, a question was asked in our Houses of Parliament, and this little controversy caught the attention of some people in China and at the Northwestern Polytechnical University in Xi'an. They decided they were going to start work on EmDrive. Now, this particular group have a lot of experience in developing and flying microwave ion engines. They were in fact brought into the Japanese Hayabusa mission when a problem arose on the return journey of this particular asteroid mission. So they know all about microwave cavities, and they quickly understood the physics and worked out the engineering. That they have some quite significantly effective test chambers over there, because they actually test flight thrusters. And in April 2010, they revealed they'd measured 720 millinewtons of thrust for a 2.5 kilowatt input. Now, this actually is the highest published thrust to date. They published a peer-reviewed paper in 2012 and subsequently went on to do some other very interesting work. You should read their papers very, very carefully to understand the work that's going on in China. Now, in Russia, the first we heard about work there was in 2009. I was actually asked to comment on a report in Pravda that they had flown a perpetual motion machine in their Yubilini satellite. Now we looked very carefully at this and decided that if indeed it was an EmDrive thruster, it was probably operating around 8 gigahertz and was powered by what is effectively the standard X-band 40-watt tweeter. I've already mentioned that we caught the attention of the American defense business with our demonstrator thruster, and we attended a meeting in 2008, and this kicked off our long-standing association with America. And we did in fact complete a flight thruster contract with Boeing in July 2010. You can see in the slide, first of all, a picture of the Chinese experimental thruster. Interesting in that instead of a loop, here they use a waveguide slot input. And below the classic picture of our demonstrator thruster. So once we completed the initial experimental program in the UK, we carried on doing a lot of theoretical work and some additional experimental work. Tackled the problem of simply turning a first generation thruster into a second generation one by using superconducting cavities. Now, there are a lot of problems with the IPCO substrate mounting. This is the so-called high temperature superconducting material we use. And I've mentioned the work we did solving the Doppler effect problem with accelerating the cavities. Now, along with the sort of this basic engineering work, we carried out quite a number of mission studies. Presented one at the IAC conference in Toronto, where we described a single stage to orbit spaceplane and an interstellar probe. We wanted to show how wide-ranging the applications for EmDrive were. And they were, and they are, very wide-ranging. One of the commercial application studies we did was for the Shell company, and that was for marine applications. We introduced the concept of amplitude modulation to help overcome the Doppler shift problem. We kept a flight thruster back in the UK and loaned this to a couple of experimental groups, and we've given continuous support to a UK government research organisation. Interestingly, we were also granted an export license to export the technology to Israel. And basically, we monitored as much as we could all the various efforts that were going on around the world, and now and again, we helped out with theoretical understanding and tried to assist some of the groups to appreciate all the challenges that developing EmDrive produce. Now we've got to a stage now where patents have run out, and some of our NDAs have also expired, and therefore we can publish much more of our early work, including technical reports and descriptions of our design methods. Now, EmDrive did not go unnoticed by the press, and in particular, you can see three press reports identified on this slide, which claimed to be reports on in-orbit tests. I've already mentioned the Russian Pravda article, and this has been updated since with their Cosmos series of satellites. Cosmos 2499, I believe, was the last one that was reported on. In America, somebody, I believe it was a NASA employee, leaked the information about the X-37B spaceplane to IBT, that's the International Business Times, and that they did an article on this in November 2016, after carefully checking the sources, I understand. This was rapidly followed by a report in the China press later that year, and this was actually a press conference given by the Chinese Academy of Space Technology, where they claimed that they were flying EmDrive in their Tiangong-2 space station. Okay, so whether these reports of in-orbit tests are completely accurate or not, I don't know. My understanding is that the sources are quite reputable, and really I believe that we can expect a few more reports to be released into the public domain over the next few years. I mean, gradually the security blankets will be lifted from this technology, because it will become more and more noticed. So we'll now turn to look at the results of some of our mission studies into the applications of EmDrive. We've done quite a lot of these over the years for all sorts of different clients. But we'll start with the first generation applications. These are for uncooled thrusters. Typical Qs are around 50,000 with specific thrusts around 0.3 of a Newton per kilowatt. And you can see here on the left is a 12U CubeSat, 50 millinewtons of thrust, operating for typically 5 years, would enable you to go to Mars or indeed fly out to Pluto. A very simple satellite of this nature with EmDrive propulsion simply opens up our backyard to all the science missions you want. If you look at GeoComSats, and these actually were the first commercial application we looked at, you take a typical ComSat, replace the primary and secondary propulsion with EmDrive, and you get rid of half the mass, because typically half the mass of these satellites is propellant. And of course, because you're no longer reliant on propellant for attitude and orbit control, you can roughly double the lifetime of any satellite, which should be attractive to the operators, if not to the actual manufacturers of satellites. So life gets a little more interesting when you look at the superconducting thrusters, and in this case we're looking at the second generation, which are straight liquid hydrogen cooled superconducting thrusters with no compensation for Doppler shift. So the accelerations are quite low, down to 0.05 of a meter per second squared, but we're getting pretty substantial specific thrust at typically 470 newtons per kilowatt. And just to illustrate the wide range of possibilities here, we move from, on the left, a very small UAV demonstrator, mass of about 60 kilograms, battery operated, short flight time, very simple, and actually demonstrates that these things can fly. At the other extreme, you have a 500,000 ton supertanker, and using complete closed loop cooling system, you can still improve the specific thrust of a tanker of this nature by about a factor of 3, as you can see from the figures that we quote here. So life gets even more exciting when you look at third generation applications. Now here we've used compensation for the Doppler shift problem, and we can accelerate up to typically 1G without losing too much specific thrust. We're running at specific thrust here of approaching 4 kilonewtons per kilowatt, very substantial. And if we look at the applications, on the left we see a personal air vehicle. And because of the third generation compensation technique, we're now doubling up on the cavities. So we actually have an 8-cavity thrust frame, giving us the classic drone type control using four thrusters. Here we have takeoff mass approaching a ton, two-man air taxi type of vehicle. It only uses liquid hydrogen, so it's a green renewable fuel. And very importantly, this air taxi is a true air taxi. It enables you to actually fly from basically outside your house to anywhere else you want to go. You no longer have the problems that any prop-driven air taxi would have when you're flying in what are called urban canyons. Again, any helicopter pilot would tell you you do not fly into areas where the airflow from your downward props is going to be at all restricted. You tend to drop out of the sky if you do that. So a very usable personal air vehicle. The personal space vehicle on the right is absolutely fascinating. We were asked to see whether we could actually take 3 men to the moon and back again in a single vehicle, effectively doing what Apollo did. And yes, we came up with this vehicle, launch mass just over 10 tons. It doesn't accelerate very fast. It keeps it down to 0.01 of a G. Which does actually enable it to be used for the end market, which is aimed at space tourism. So we needed to produce a very gentle flight regime to the moon and back again, which actually will take of the order of 72 hours flight time. Absolutely fascinating mission study, and demonstrates the enormous advances that EmDrive give you in terms of transportation in space. One of the first applications that we looked at was in fact an unmanned vehicle. In this case, we wanted to look at how we would produce a heavy launch vehicle. And this now goes back to 2008 when we actually showed the aerodynamic test model of one of our early spaceplane concepts. Now, at the time, US Air Force Colonel Coyote Smith coined the expression that EmDrive is a space elevator without cables. And this essentially was what we were trying to aim for. The latest concept is effectively much as the original requirements were: 50 tons to geostationary orbit, fully usable 500 missions. Essentially, you simply hang the payload under the wing of this space plane, which indeed has obviously vertical takeoff and landing capability, but does have some glide capability. It's highly maneuverable. It's got pitch, roll, yaw, and also X, Y, and Z translation. So it can be used for docking and indeed for deploying payloads if necessary. It's obviously unmanned, fairly large wingspan, nearly 20 meters. total launch mass of 116 tons, of which 15 tons is liquid hydrogen. It again doesn't accelerate very quickly, 0.014 of a G, and takes something like 6 hours of continuous thrusting to get to geostationary orbit. The advantage, though, of this is that it's a very gentle flight envelope. Indeed, we restrict the maximum velocity through the atmosphere to 70 miles an hour, which means the mechanical and aerodynamic and thermal loads on the airframe are very low, and indeed it is really quite feasible for these vehicles to be manufactured by a truck company. You know, there's no real high technology needed in the airframe any longer. This is all a very gentle exercise. And the big thing, of course, is this brings the costs down dramatically, as we will see in the next application. And this application is probably the most important one for the world, and this is to be able to launch solar power satellites. These have been technically feasible for many years. Indeed, the seminal study report back in November 2011 says that there are no real technical barriers to this. The big barrier is to make them economically viable. And of that, the most critical challenge is at low cost, actually very low cost, Earth to orbit transport. If you take a typical SPS design, you need to get 6,700 tons into geostationary orbit to be able to generate constantly 2 gigawatts. Now, if you look at conventional transportation costs, you'd need 1,700 Atlas V rockets with a total cost of something like $194 billion, which is about $29,000 per kilogram. Now, the original study requirement reckoned you'd need to reduce this to $20 billion to make this particular solar power satellite viable. Now, we've obviously aimed to produce a very low cost transportation system using EmDrive, and we believe that we can bring the transportation cost for one 2 gigawatt solar power satellite down to $74 million. That is about $11 per kilogram. I mean, this is a huge reduction in cost, way below what the requirement is to make these things economically viable. And so effectively it makes solar power satellites the only real way to go for long-term energy provision for the world. The study we did showed that we'd need 134 launches, that we'd have to use airline type operation, you know, a 2-day turnaround. It'd take less than a year to build one SPS. And you'd also use the heavy launch vehicle that we described earlier to carry out all the docking and manoeuvring and indeed the deployment of various parts of the solar power satellite, mainly obviously the solar arrays. So we have a situation that EmDrive will be able to provide solutions to the renewable global energy requirement. That's quite a claim. Now, if you can get thousands of tons into geostationary orbit for solar power satellites, you can also get thousands of tons to the L1 point between the Sun and the Earth, and you can deploy orbital sunshades. Indeed, if you want to combine the SPS function and the sunshade function, you could do that, but you'd need laser power transmission to geo and then microwave from geo to Earth. The most important point about deploying orbital sunshades in this manner, apart from the fact that they can be done relatively cheaply, is that you have control over the actual amount of shade that you're putting on the Earth. In fact, you can have minute by minute control because you simply change the attitude of these huge sunshades using EmDrive thrusters for the AOCS functions. So this is a completely controllable way of starting to shade the Earth, and this is necessary because we don't really know what's going to happen when we start shading the Earth, and you need to be able to do it step by step, understand the results of what you're doing, and be able to be in total control of shading. But the interesting point about it is that this would be, first of all, probably used for localized shading. And you can actually see the economic advantages of, for instance, a city deciding that they would actually like to have a lot more shade during the day to keep the inhabitants of this city a bit cooler. So you know, you can imagine cities actually funding their own sunshades. Now, if we're looking at global warming problems, you can also envisage international efforts to start shading the polar regions so that we stop melting the icebergs. So what we have is that EmDrive can enable solutions to probably the most important problem of our age, which is global climate change. This I think is a very important aspect of the future of EmDrive.
Okay, guys, give me just a moment. Let me plug everything back in. Okay, so I think the first thing that we should do, and you guys can all hopefully hear me okay, the first thing we should do is give Mr. Roger Shoyer an enormous hand. Thank you, sir. Thank you very, very, very much. That was a remarkable presentation. I owe everyone a giant apology for the microphone issues. We did not know. We actually found a solution during the call, but we would have had to restart. So let me ask Roger to unmute. We'll go into the Q&A section.
Yeah, can you hear me?
Yes, I can. And can you hear me as well, Roger? Wonderful.
Yes, certainly. Yes. Yeah.
Oh, okay. Well, yeah. So let's do Q&A now. And let me see. So who would like to go first? Again, guys, raise your hands if you have a question. Oh, okay. Will, would you like to go?
Yes, the EmDrive showed that the end plate was superconducting. Does it matter if the whole EmDrive is superconducting, or you just want the end plate only to be superconducting?
Okay, that is a very good question, and one that I can't answer in any great detail, but I can tell you that different designs have been built and tested. And of course, if you have a completely superconducting cavity, then it works the best, but it is the most difficult to produce. Putting IPCO coatings onto curved surfaces is a very specialized business. It has been done, and it does give you the best performance. One of the probably better ways to go for early work is to take the flight thruster geometry, where you have actually two, you have a flat small end plate, and you have a flat central section of the big end plate. So you do in fact get quite a good superconducting performance out of that. Just to let you know that the early one that we did, the first superconducting thruster, was built entirely out of flat flat elements, which was not easy to do, but it did work, and we were able to do a full super.
Okay, it looks like, again, these might be the bandwidth issues that Roger had mentioned having. That's why we had to do the video. Yeah, and he disappeared. Okay, he will be back in just a moment. It looks like he dropped off. Okay, let me see. So in the meantime, does anybody, I think,
Can we crank up the audio?
I'm sorry, John, the audio was too low for you?
Can we crank up the audio? I can hardly hear.
You might look at your speakers. Take a look at your speakers and see if you can get them on theirs.
Roger, maybe.
Actually, sorry.
I got a Bluetooth here, but I don't know how to connect it.
Okay. I'm gonna mute him out. Let me see. Sorry, Roger is back. Roger.
Yeah, I lost you momentarily there.
Oh, no worries. No worries.
It's a long way across the Atlantic.
I'm sorry. Where were you at again, sir? You had more to add, I believe, right?
Not really. It's just that there are a variety of ways you can build a superconducting thruster, and it doesn't always have to be totally superconducting.
Okay.
Well, I'll leave it at that.
Let me go to Michael Boyd then. I will ask him to unmute, sir.
Hello, can you hear me?
Welcome back, Michael. I hear you wonderfully.
Yes, certainly. Yeah.
Okay, so I have some general questions. When I got up this morning and I put my coffee, my cup in the microwave oven, and it warmed up real nice. In some of your presentation there, you were showing vehicles and stuff where there would be people near these, let us say, RF sources. I'm curious if you've considered any of the harmful effects of microwave radiation on biological entities like us.
Yes, again, a good question, but I've spent a large part of my career on high power microwave devices. And it is always a question you have to address. You do not handle high power microwaves unless they are completely isolated, and you inevitably have checks. You have field meters around you to make sure that you don't expose anybody to microwave radiation. I mean, it is quite dangerous. You don't need many watts to give yourself a cataract or to blind yourself. And as you quite clearly mention, if you have too high power and the typical microwave oven is only 750 watts, you can cook things. And so, yes, you do have to be extremely careful. Yeah.
Okay, so those are some of the challenges that you would have to address in commercializing the application of technology is essentially what I'm hearing you say, correct? That's down the road.
But these are, sort of, sorry?
That's addressing that.
These are well.
Sorry.
Yeah, these sort of problems are well understood, and we've handled high power microwave devices many times before.
So the other question I had also had to do with the yttrium, barium, copper oxide superconducting material that you are using. My understanding is they've found superconducting materials, higher temperature superconducting materials, and there is some evidence of using microwave radiation to achieve room temperature superconductivity. Have you considered any of those recent advancements in superconductivity?
Okay, I lost you again briefly.
Okay, no problem. I'll repeat my question was essentially there's been some recent breakthroughs in superconductivity, other materials besides yttrium, barium, copper oxide, which is basically superconducting. My experience with it is it worked okay at liquid nitrogen temperatures, and I notice you're using liquid helium. But my understanding is they've made higher temperature superconductors now, and they've even developed techniques using microwave radiation to achieve room temperature superconductivity. Have you considered any of these new technologies?
Yes, certainly room temperature superconductivity is a target, and I'm aware of the work that's going on, some work that's going on there. But at the moment, the only thing that's in the public domain is actually using liquid hydrogen, not liquid helium. And the reason for liquid hydrogen is that once you've used the liquid hydrogen to cool the IPCO down, the boiled off hydrogen gas you can use in a fuel cell to produce the power. So it's there are clear advantages in liquid hydrogen, but as soon as room temperature superconductivity comes along, that'll be great. It'll solve a lot of problems.
I'm just curious, what's the temperature of liquid hydrogen? I know helium is like what, 5 or 6 degrees Kelvin? What's hydrogen?
20 degrees.
20 degrees Kelvin.
20 degrees K.
Okay. Okay.
Yeah,
Thanks for all your
degrees.
answers. I appreciate it. That was helpful.
And thank you, Michael. Okay, let me go to Benedek next. Sir?
Hi, can you hear me?
Yes, wonderful. Thank you for joining us, Benedek.
All right,
Yes.
so my question is about energy conservation. You need a lot of energy to go into orbit, and used energy is conserved in the EmDrive. And in the most ideal case, all the energy pumped into the cavity turns into kinetic energy. Now, where would a spacecraft store as much energy as needed? To get into low Earth orbit of 1 kilogram mass, you approximately need the energy of 8 kilograms of TNT. So how could you passively store as much energy as needed?
Okay. Let's do that in two parts. First of all, you cannot use all the stored energy in the cavity to produce kinetic energy. Otherwise, there's nothing left to produce thrust. So you need to keep a balance here. And typically you'd run a cavity at about, say, 50% efficiency. So you're turning half the stored energy in your cavity into kinetic energy. Now, the simple answer to your question is how you get things into orbit, and how do you carry the energy? Well, first of all, you store the energy as liquid hydrogen.
Oh, and it looks like we may be losing Roger again. Yeah, Benedict, I did actually see your question earlier in chat. And so it is, thank you for asking that. And he should be back with us in just a moment.
Liquid hydrogen has more energy per weight than TNT, but I still don't think that there could be enough stored. So.
Well, I mean, I think you're making a very good point, right? When you're looking at the efficiency and stuff like that, then it does become a challenge. So yeah, I think you're asking some difficult questions about energy and energy storage and how you would use that. So it's good to ask that. It's good to address those questions, and hopefully that Roger will be right back with us. Okay, yeah, see, it looks like he may have to restart his connection here, because it still lists him as being in the conference. And everybody, I should apologize to you for the challenges with our connection. Okay, it looks like he's dropping off, and he should probably be back in just a sec. Jeremy, how are things going for you over in YouTube land?
Good. Hey, you should probably have him do audio only if he's having trouble with the streaming, the upload, and the video, probably killing his bandwidth. So maybe when he comes back, we'll have him do audio only.
We'll try that. We'll try that.
Sure.
How many folks do we have on our YouTube channel today?
Oh, it's quite a bit for Easter Saturday. 128, about 130.
Yeah.
Fluctuating. Cheers, everyone in the audience.
Well, and thank you for streaming us on Alien Scientist. Just as a reminder for everybody, Jeremy runs the Alien Scientist channel, 100,000 subscribers. He is doing, you're doing broadcasts all week long, right? I mean, you've done 3 or 4 this week.
I interview a couple different guests. I try to interview different people too. I'm trying to get people who come on your conference to also, cross platforms a little bit too. I interviewed you the other week too, so we could talk, because you don't get enough airtime during the conferences. It's usually all our guests. So I gave you a chance to take the floor, and that was great too. So thank you for joining me for that. And we also do like a meeting with our engineering team. Probably like once a week we'll get together on a Zoom call all together and just discuss stuff live. And in addition to some other private chats that we engage in on the side behind the conferences for the engineering side, for the actual lab side of this,
Okay, and it looks like Roger is actually coming back in. That's why I got, or he was attempting to. It looks like he's not back in quite yet. But yeah, no, that's good advice about the bandwidth. We'll see if he can stop his camera.
Yeah, we got a ton of new viewers from when I went on my friend's show, because my friend Ian is a regular on Tim Pool's podcast, which is a big show on YouTube, and I got a big viewership. It's like almost like going on Joe Rogan now that Joe Rogan's like not even on YouTube anymore, really. So that's cool. YouTube is kind of an interesting landscape lately. So I'm trying to rework a lot of my content to include more experiments from the team, and also more short videos and edited summaries, which I'm going to get into very shortly.
Okay. Yeah, it looks like. Yeah, so it looks like, again, Roger is back, but he's still having bandwidth issues. You know, some of this Wi-Fi connections cause a lot of trouble for folks, too. Not as bad as it used to, but.
Yeah, I always recommend using a landline, you know, on Ethernet cable.
Yeah,
Plug in
that's-
direct. That's like the best way to go.
Yeah, that's the.
I seem to have reconnected with you all now. Sorry about that.
Welcome.
You were talking about how you store the energy to get into orbit. Well, simply the energy is carried in the liquid hydrogen tanks. And if you do the calcs, and these are shown in some of the papers that I've written, you can see there's the sufficient energy to get you into orbit, albeit slowly.
Wonderful. Now, Roger, I'm actually going, if you want to do it, I'm trying to stop your video. That may help your bandwidth. Jeremy Reese has suggested that. And I should apologize, I'm having trouble finding you. We got so many folks in today's conference. We have 44 people in the room with us. Oh,
So did you get that answer?
yeah, oh yeah. Nope, I got the,
Good,
yeah. There we
Yeah,
go.
I got the answer. I will quickly run a calculation. I don't think hydrogen is energy dense enough, and speed doesn't matter. So even if we discount air resistance, you need a fixed amount of energy to get into orbit, and for that energy, speed doesn't matter.
Yeah, and that's definitely something.
So
Oh, I'm sorry.
yeah, can you hear me now?
Yeah, I can hear you
Yeah,
now.
yeah. If you can hear me now, yeah, you basically have to do the calculations of getting something into orbit, a mass into orbit, effectively going back to Newton's equations, and if you do that and do not try and solve it using the rocket equation, then you'll be able to come up with the correct energy requirements. I think the big problem is that everybody is used to using the rocket equation, and of course that doesn't apply to EmDrive. You don't have to carry the fuel with you, or you don't have to carry very much fuel with you, and because you're not throwing fuel out of the back of the rocket equation doesn't it just doesn't apply. You have to go back to basics and calculate the energy from simple Newton's equations and work from there. Try it, you know, I mean,
Yes, that's what I did.
Just try it out.
Yeah, I just roughly have to go 8 kilometers a second, and that's the energy I calculated. I didn't even count the potential energy, gravitational potential energy. That's an additional over that 8 times TNT level.
Oh, okay. Well, Benedict, thank you. Let me go. Jeremy, do you have any questions in the YouTube channel?
Yeah, I have a question for Roger. What are your views on space-time, and what do you think space-time is?
Well, space-time is actually as Einstein defined. It's essentially combining the 3 dimensions of space with the 4th dimension of time. Now, that's fine, you know, but it really doesn't apply to EmDrive. EmDrive is simple classic physics. You don't have to, well, not until you get towards very high velocities do you have to take into account special relativity. And at that point, you have to, the correction that appears in the thrust equation, you have to take that into consideration then. So you'll never, for instance, get past the speed of light. In fact, you'll get about 70% of the speed of light, and that's as fast as you'll get. But you know, it's up to these relativistic spacecraft velocities. It's really all Newton's laws.
All right, thanks. One more question is, what do you think? What are your thoughts on Martin Tajma?
Yes. Well, I have to say that in October of 2017, I did explain to him why the NASA cavity was not going to ever give any thrust. And bless him, he spent 4 years proving that I was right. You know.
Good answer.
Yes. Jeremy, thank you, sir. Let me go to Plane C. Plane C, and that's, I believe that's a pseudonym. That is not hopefully not a real name. Where are you at, sir? Plane C had a couple of questions. I think he was asking about practical. Roger, if you're still with us, oops, it looks like Roger might be. Even without the video, he's still having bandwidth issues. So I wonder if that's a Wi-Fi problem. So we'll do Plane C next, and then Will Reichen had another question. And I should ask, are you guys all doing okay? I should apologize for some of the bumps on the road today.
Okay, did you get that answer?
Yes. Oh, and you're back. Wonderful. Thank you, Roger.
Okay, right.
I did.
It
Actually,
comes and goes.
Oh, no worries at all. I just appreciate you being with us.
Was he not
So
finished?
we had another question. Plane C had asked. So he was wondering, I guess he was wondering about the next practical steps to test the concept. And he'd also asked about commercial space industry interest. Okay, it looks like Roger. Are you still with us? Okay, and it looks like he dropped.
Yeah, I'm back again. The next steps. Well, I have to be careful here because there are clearly steps that have been taken that are not in the public domain. But if you move from what's in the public domain, then the next step is to fly first generation spacecraft, first generation EmDrive thrusters, and then fly small UAVs, small flying vehicles for second and third generation. That's the sort of sequence of things that will become known over the next few years.
Wonderful, thank you. Let me see. I believe actually Will Reichen had another question. Will. And then we'll go to, after that, we'll go to Gravity Alchemist. But it looks like Will's having.
Sorry, I had to find a cursor. My question is, you discussed the second generation and jumped to the third generation, where the third generation was AM modulation. So my question is, are you looking at multimodal in the third generation? Is that a combination, or is that completely different physics?
Okay, the difference between the second and third generation is obviously a much quite a large increase in complexity. What it does give you is much higher acceleration whilst maintaining high levels of specific thrust. Now you can actually combine all three generations if you want to, but it's essentially the third generation is essentially, and the physics is still the same. It's just that you're employing, well, first of all, you're employing a well-recognized radar technique of using circular polarization to enable you to control the cavity length and also the frequency. And I have to admit, at this point, this was essentially a Chinese idea. I'm not going to say any more about that, but yeah, you know, but the physics is the same. There's no change in the physics.
If you're using AM modulation, then does that necessitate the cavity to be much larger than the microwave cavity?
Sorry, the AM modulation. I didn't quite get
the third generation. So so my question is, does that mean that you need a larger cavity for the? Yeah.
Yeah. Okay. I understand. No. The size of the cavity is really dependent on how much thrust you want to get out of it. So you tend to make cavities. The size of the cavity is dependent on the frequency, and so if you want very high thrust, you go down in frequency and higher and larger cavities. We've gone down to 500 megahertz cavities, and these are pretty big. But you know, like all in engineering, if you want to get a lot of power or thrust out of something, you inevitably have to go bigger. But again, it's not a question of whether it's first, second, or third generation. It's really how much thrust you want to get out of the beast.
Wonderful.
Okay,
Well,
so you're using the AM modulation so you can dump more energy into the cavity. Then essentially is what you're saying.
Yeah, the AM modulation is
are easier to handle. So
yeah, the AM modulation enables you to reset the if you like the cavity extension, and during the reset period you simply switch the power to a second cavity. So you do need two cavities in a third generation setup, and you're switching continuously from one to another.
thank you.
Thank you, Will. Okay. Let me go to Gravity Alchemist next. Sir? Okay, sorry about that.
I'm sorry. Okay, do you hear me now?
There we go. There we go.
I'm sorry about that. Hey, Roger, this is a great presentation. I really appreciate it. You've got some great nomenclature, and I'm gleaning a lot from all that information. I'm kind of new to science, so bear with me. I have a big curiosity. You had mentioned, one of my curiosities was same as the last question about how much thrust. I think you'd mentioned you tested one that has 720 millinewtons on about 2,000 watts of power. And I'm trying to correlate that into my little brain about what kind of SI unit that is. In other words, is that something that's just scaled up in order to get the kind of thrust that's needed to move some of these large masses around? Can you elaborate a little bit on that, if you would?
Yeah, certainly. The figures you quote are actually from Chinese work carried out at the Northwestern Polytechnical University by Professor Yang Zhuan and her group. and they are indeed the highest published specific thrusts. Not the highest specific thrust, they are the highest thrusts. Now these were done back in 2010, before everything went quiet, for fairly obvious reasons. But essentially what you do is you scale up by increasing the Q of the cavity. So Professor Yang's cavity was pretty much like our flight cavity, around 50,000 Q. Now, if you go to a superconducting cavity, you go up by many orders of magnitude. I think the highest Q values people have got are probably about 5 times 10 to the 9 or even higher. So of course you multiply the specific thrust by that amount. You hit all sorts of problems, you know, like the Doppler shift due to acceleration. But again, it was the Chinese that actually contributed significantly to that solution. But you will not find in the public domain anything higher than those original Chinese results of 2010. And there's clearly obvious reasons for that, which I'm not going to go into.
Okay, well, all right. Super. Now, this Q that you're talking about is the Q. How do you determine is there some kind of resonant, or you said you adjust the frequency in the cavity in order to get the maximum thrust out of it? Is there some kind of formula that I missed the first part of your presentation, I'm sorry, but in other words, the Q, it's based on the volume of the cavity and partly has to do with its shape. The other, you know, of course, but I was wondering why the speed of light changes at one end of the cavity also. You said 90, slower than 90% the speed of light at one end of the cavity.
Yeah, okay, let's sort of take each question at a time. The Q of the cavity is dependent on the dimensions, but primarily on the resistivity or the surface resistance of the material it's made of. So to go superconducting means you reduce the surface resistance inside the cavity by many orders of magnitude, you increase the Q. And all this is sort of, you know, standard formula out of microwave textbooks. Now your second question was, actually, what was your second question? It was, I know, it was to do with the speed.
Yes.
Yeah, it was to do with the speeds inside the cavity. Well, first of all, the speed of light doesn't change. I mean, you know, we're not changing C, but what we are changing is what's called the guide velocity, or sometimes it's called the group velocity. And this is actually the speed at which the energy and the momentum inside an electromagnetic wave is carried. Again, this is standard equations, you know, going way back to the 1950s. And you know, it's nothing mysterious about this. For instance, there's a well-known example of a very, very slow wave guide velocity. If you look at your microwave oven, you'll see inside the behind the glass window, there's a very small mesh, and the size of the holes in those mesh are designed so that actually the propagation velocity, the guide velocity, is 0. Otherwise, you'd fry. And you know, that's because in technical terms, the hole size ensures that you are working in cutoff conditions, and the traveling wave cannot travel through them. And again, this is all well defined in microwave theory. It's why waveguides have to be a certain size to carry a particular frequency. So it's not the speed of light that changes, it is the guide velocity, which is always a fraction of the speed of light, depending on the size of the cavity.
Wonderful. Thank you, Roger. And thank you, Gravity Alchemist. So let me go next to Jacob Helby, sir.
Hey, Roger. Quick question here. So I'm just wondering if you've ever considered the effects of having more than one microwave source inside the cavity. Have you set that up in any of your designs?
Well, flight thrusters always should have redundancy built into their system. So yes, we have considered that for flight thrusters, it is not a bad idea to have two microwave sources. It's good old spacecraft engineering, building redundancy wherever you can.
Well, I guess maybe not so much redundancy, more so having two different opposing sources on opposite ends of the cavity. Maybe if you can play with the frequencies of each end, you might potentially see more thrust. I'm just wondering.
Not really, no. Your cavity is very carefully designed and sized for one particular frequency at the particular mode you've chosen to operate in. So bringing in another frequency source it will not affect, really won't give you any advantage. In fact, it's definitely going to complicate the system. It's tricky enough getting the cavity to work with one source. You don't really want to bring in another at a different frequency.
Okay, thank you.
Yeah, thank you. Let me go back to Will Riken next. Will, go for it, sir.
Yes, you mentioned the sapphire window and the WaveECO, but what was the thickness on that? And also, does the thickness of the superconductor make a difference? And have you tried other superconductors other than WaveECO?
Okay, the thickness of the actual superconducting film is not really that important as long as it's thicker than the skin that you need. Microwaves only travel very, very close to the surface of the conductor, and the thickness of the, if you like, the microwave currents, or the depth into which they go, is known as the skin depth and this is always very, very small, measured in microns. What is important is to ensure that the substrate thickness, in this case it's sapphire, is thick enough to be robust enough to withstand the forces that you're applying as soon as you start putting power into these things. So you need some fairly thick substrates, but the actual thin films themselves are very thin, and as long as they're thicker than the skin depth, that's fine.
Wonderful, wonderful. Well, thank you again, Roger. Let me see. So we have time left. Does anybody else have questions? Mark, why don't you go ahead, sir?
I don't know if this was asked already because I did have to step out for a little bit, but have you read the paper that was in Popular Mechanics about Martin Tajmer's replication of your experiment from earlier this week? Do you have any comments on that?
Oh, actually, yeah,
Yes,
Jeremy
yes,
asked about
certainly.
that.
Okay, I'm sorry. I didn't. I'll
Yeah, I
check
mean,
it then.
well, if you want some more details, I can give you some more details, because you know, the NASA cavity, which is the basis of Martin's work, and indeed at least three other organizations' work, is fatally flawed. It's a flat end plate cavity for a start, you know. So if you do the simple geometry as shown in, I think it was slide slide 9, I think it was, you'll see that by the time you get to a Q of about 14, you've got a wave front phase error approaching half the wavelength. You know, the whole thing collapses. You're never going to get the traveling waves in a flat end plate cavity. And there are many other problems he has. I mean, he claims a QU of 23,000, which is a nonsense. What he's doing is just measuring the Q of the input loop, because if you read the paper, you'll see that he uses a single port measurements technique. He claims a 45 dB return loss. You know, that's not feasible when you're trying to balance a loop Q, a very high Q loop, and a very high Q cavity. You know, by the time you get the impedance match correctly, we've never got more than about a return loss of 20 dB. So you know that the cavity that he's working with is not a traveling wave cavity. You know it's going to give you zero thrust. Three other competent organizations have also found this. And I advised one of them actually many years ago of all the reasons why a NASA cavity wouldn't work. And not saying it was my fault, but it wasn't long afterwards when NASA abandoned that work. So you know, yeah, I mean, what Martin has done is put in a huge amount of effort into basically proving that the principles behind EmDrive are correct. Because if you don't follow the correct principles, you don't measure any thrust whatsoever. So I'm quite grateful to Martin, actually. I would never have done all that work myself, and I don't know of anybody else that would have put all that effort into it. So that's great. Yeah.
Oh, sorry, Mark, I just muted. Did you have? Okay. Oh, Mark was just saying thank you, and I should say thank you as well. I should apologize, Roger. It's 2 o'clock. We're at the top of the hour, so I want to thank you again.
Right.
Thank you so much for joining us, and everyone, please put your hands together. A giant thank you for Mr. Roger Shoyer. Roger, your work with the EmDrive is truly legendary, and I cannot thank you enough for joining us to present about it today. Okay.
Yeah, well, thank you for having me and for listening.
Thank you again, sir. Okay, so let me see. And now let me introduce you to Amar Vakil and John Clymer. Both of these gentlemen are career electronics engineers with decades of experience. They've been collaborating on a research into quantum gravity and multidimensional models of physics using computer modeling. Amar also spent several years talking with John Searle, Tom Bearden, and a few other notable figures in alt science. And he's tried to integrate and build off of some of the insights they shared with him where it's appropriate, while also developing new models and new approaches to quantum gravity and propulsion. Okay, so Amar, are you with us, sir? Let me hand it over to you.
Well, I'm just going to get the PowerPoint. I think I talked to John on the other, John's there, and I'm going to get the PowerPoint up right now. I'll see if I can share it.
Perfect, go for it, sir.
Give me a sec, and bear with me. I think John's going to start the presentation, but I think he needs to, let me see if I can.
you'll
Should
control
I
the
share it or
PowerPoint.
should he? Let me have John share the slide first because he knows what to do. Do you want me to get John on the speaker there? Hang on a second. John, you're there? He needs to get on. See if he can share the screen.
Okay, no, okay.
Can
Somebody
you
tell me.
the share screen on
where
the
to
bottom?
find- Yeah, I'm on there. Now what?
There's a share screen on the bottom, and you want to click on that.
I did. Now what do I do?
I can do it if you like.
Yeah, Mara, it might be better if you do it. It looks like
Okay,
you're
I'll do it.
connected.
Okay, that's all right. I'll go ahead and put it up. Okay, here we go. Hang on a sec. Okay, so oops, let me go all the way to the top for John. So John, when you say next, I'll go ahead and move the slide to the next. Can you folks hear me?
Yeah, you sound
Okay,
wonderful.
I am on speaker. Okay, sorry. So John, when you say next, I'll just move to the next screenshot. Next slide, excuse me. So this is the title, and John is starting out, and then I'm going to start on
Why
slide.
don't you go to slideshow?
Oh, I see what you mean. Okay, hang on.
Go to,
Yeah. I
go
hear.
to slideshow.
Yeah. Hang on.
Anyway, everybody hear me okay?
Yeah, there it is. Okay. Yeah, I can hear you, John.
Okay,
I'm going to mute.
my background, can you hear me? My background, systems engineering, system science, and systems analysis, that sort of thing. And I wanted to kind of give you a context. This is a whole lot different than you guys are used to hearing, I'm sure. It's going to be out there. But when we get through, hopefully you'll see how it might be very useful to a lot of things we're interested in doing. And this technology that I've got, Amar has, started about 2000. I was working on a problem for the U.S. Navy on Standard Missile 3, which is a design to go out and knock down re-entry vehicles. And so I developed a simulation model that modeled the sensor, which was an IR sensor array. And the problem they had was to detect the target and keep it within the cone of the array. And so if you're very far away, yeah, the target's in there, but you may not be able to identify it. And then as you get closer, yeah, you can identify it, but now it's going out of your field of view. So I developed an algorithm that worked on detecting the target as early as possible, allowing for ambiguity. And then as we got closer, we got more and more accurate. And the accuracy of the identifications of the various objects were used to control the guidance algorithm. So the most likely target was the one that you were aimed at. And this worked extremely well. And in the process of doing this, I made a discovery. And that is that the sensor data that we were getting from the IR basically amounted to a whole bunch of measurements from the IR array. And this amounted to what we call an n-dimensional vector of data. And what had to happen was that we had to map this data, raw data, into what I call features. Features are actually identify what's out there. And this is a classical problem you have in data mining. What are you doing?
Just a sec.
Why are you changing the slides?
No, I'm not. None. All right. Sorry about that. Okay.
I'm not ready for that. Anyway, so what I discovered was that the feature space was a smooth manifold embedded in a higher dimensional space. And so this got me into differential geometry and tensors and K forms and general relativity, electromagnetism, quantum field theory, mathematics involved in trying to make sense of all that. And it was one of these, you guys are probably familiar with, once you get onto something, you just keep going and going and going. Well, okay, that was great, except that when I got all through, all I had was a model of mathematics, and I couldn't put it all together. I couldn't integrate it. Well, I'm still working on that. Right now, I'm working at Minkowski's original 3 papers where apparently he attempts to do just that. Anyway, that's one thing. And then Amar and I collaborated, and we started looking at papers where there were actual experiments performed. Experimenters were doing what I call disturbing matter, and it resulted in what I call some kind of energy field coming out of the ether and basically regulating whatever the change was. And we saw this, I don't know, we saw many papers where this was happening. The talk we just heard could possibly be one of those, where if you create a negative resistance, you can pull energy out of what I call the information universe. And that's where you might get extremely high Q. I mean, it would be astronomical because the energy would be coming from outside. Okay. So we call this the information universe. And this talk is going to basically, as I said, exploring the combined material and information research to discover information universe, to discover new physics. And we've so far got 3-4 papers out there where we talk about this. Okay, go to slide first slide.
Okay.
Okay, so the objectives. We want to, hopefully by the end of this, have you understand the fundamental what I call intelligent adaptive concept. And this in system science is where you have a network of intelligent agents. That means they're capable of adapting and learning, and they're connected. And in our experiment, we're looking at the idea of a disturbance in the information in the universe. It requires adaptive learning to control regulation. And the other thing is that Amar has pointed out is that you can have a disturbance that can be very dangerous. We know the experiments that have blown up when people tried to disturb some matter, and the result in the information universe was catastrophic. So that means that you got to have some way of controlling the disturbances that you're applying to avoid a catastrophic outcome. I think that what we're going to be talking about here applies to all kinds of research that's going on right now. And I suspect the EmDrive would just be one of them, where you might want to use something like what we're going to talk about to tune the operation of the system in order to maximize the Q, and therefore the thrust. Okay, so this leads to the second objective, which is to understand interactive concurrent process model, which will explain the information universe. And this is based on system science. And I've written 2 textbooks. I've got 75 papers on ResearchGate that talk about, the evolution of this idea. Okay.
Excellent.
Okay, these are the main topics. We want to convince you that the information universe actually exists. So we're going to present some evidence and a description of the combined information material universe as a feedback control system. Many authors, for instance, Lee Smolin, has a what is wrong with physics? What is it? Trouble with physics. And Sean Carroll came out with another book where basically it's saying the same thing. And both of them have concluded there's something else. And we call it the information universe. And that the information universe is interacting with our material universe. And that it basically created it, it maintains it, and regulates it. And we think that the combined system would probably become unstable if there wasn't this control going on. Okay, the second topic is I call CSS, which is operational evaluation modeling for context-sensitive systems. And I've got a simulation of the information universe. I don't know what that means.
Is there a
Yeah, these papers, some of these papers have been peer reviewed. The ones that are in the systems engineering, system and cybernetics, and INCOSE, International Council on Systems Engineering, and some conferences. Anyway, so the OpEMCSS simulation of the information universe, I'll show how it is capable of doing rule learning to regulate the material universe. So basically, we start off with the total chaos in the material universe, and we have a collection of processes that are interacting, talking to each other, and they learn the rules that basically reduce the chaos down to basically hydrogen atoms. Okay, and of course, what that does is it reduces entropy. As you'll see, we measure entropy in the system, and you'll see that there's quite a reduction in entropy, and we'll talk about that more. Okay, description of the quadrupole experiment. This is our idea. Okay, we're going to try to test some of these ideas, and we've got some software that I've developed and Amar has developed, which we think is capable of cracking this problem.
next slide?
So let's go. Next slide.
Okay. This is, let's
Right
highlight
in
it.
the middle of my slide. This is all new to me. I'm probably messing this up, but I'm trying, very trying, right? Okay, so next we're going to talk about that the IU actually exists, and that basically the research that we've uncovered indicates that the information universe creates energy fields of some kind to regulate disturbances in the material universe. And these experiments have revealed that you can see heat, electric fields, gravity, propulsion, quantum states, and these have all changed. This propulsion force, of course, is what we were just hearing about. That the idea is that you can pull energy out of the information universe in the form of thrust. And of course, this is a very important thing because, we're going to conquer space. We have to get out, be able to thrust all the way, to Mars and back or wherever we're going. Wonderful. Peer reviewed is bad. Okay. Solar. Okay. So examples. One of them is that's true. That's true. I don't believe in it either. Okay. Solar cell carrier multiplication is very interesting. This is Victor Klimov's work, and we had an opportunity to communicate directly with him. And basically, he a specific light wavelength shining on a solar cell can give you what they call carrier multiplication. In other words, extra electrons are coming out of the information universe. And this project has vanished behind the dark curtain. Okay, then another one is propulsion. This is Jim, and we were very familiar with this. We actually went there and watched his experiment, and he's trying to do the same thing we just heard in our previous talk, and that is to produce propulsive thrust. And my impression of his work was that our system would be a great benefit to tune his experiment to get more out of it. And matter of fact, we were watching a talk where they were presenting this to I think it was the Navy. No, it was NASA. Anyway, the question came up, that you guys could tune this. That's right, NASA. You guys could do something to tune this, but they didn't take action. But anyway, we think that our system could be used to tune that experimenter to get the maximum amount of thrust out of it.
Next slide.
Yeah. Okay, the radiator action reduces entropy. Okay. And this is another important thing. Several of our papers have looked at this. Entropy is a measure of information content in a set of messages in a system. And we have several simulations that show that entropy is reduced if you have regulation going on. regulation eliminates behaviors that are ineffective. In other words, they're not helping you. And then when you eliminate behaviors, you eliminate the number of messages that can occur. So the other thing is we studied is the idea that regulator action is when matter is present. So the regulation can create what they call entropy fluctuations in the IU. In other words, entropy landscapes. And Berlendi has got some papers on that. Where the idea was that these entropy landscapes in the IU, due to regulator response to disturbances, appear to create energy potentials in the material universe. One of them being gravity. We also know that you can get electrical fields, electromagnetic fields, you can get heat, you can get all kinds of strange effects if you start trying to disturb something. Next chart. Next chart. Okay.
I just did.
We have I created a way of thinking about it, a model, a system science model. So hopefully, if you can bear with me here, this may help us all at least be able to visualize the thing. And first, the idea basically is that we have a network of communicating intelligent agents, and that these things exist in the information universe. The idea came from Lee Smollen's description of loop quantum gravity, where he was saying that there are energy loops below the ZPE, where when these things intersect, it produces nodes. And these nodes basically create 3D space. And so you have space being space elements. Space is not continuous, but it's created with discrete elements. And I thought, well, maybe they do more than that. Maybe they actually regulate the material universe. Maybe they created it in the first place, and now they regulate it in order so it doesn't all collapse. So I'm thinking, okay, these agents are going to share messages to determine the proper regulator action at each space element. You want the regulator actions to be consistent, mutually consistent with everything that's in what I would call the landscape. So they would have to coordinate to do that. And then the agents create process threads by sending messages to each other. And these threads then periodically update the status of whatever material is at their location, and also they maintain space-time. And excuse me, I gotta take a drink here. So they do this periodically. And so basically the concept is that these processes running concurrently, each one is kind of managing one element of space and whatever's there. And they coordinate, they do a regulation, and then they all share their information in the universe, because everything basically transmits in zero time. Time does not exist there. And then they synchronize so that space-time is moving along in chunks. The simulation model that I've got shows this. So let's go to the next one. Okay. Well, this is probably an eye test, but basically all this is this is OpEMCSS. These blocks are connected. I don't know if you're familiar with extend sim, but anyway, each one of these little blocks do something, and that their aggregate is that they create a computer simulation program. So you can create just a regular computer program, computer programming language, or you can create a simulation of a system, whatever you want to do. Well, in this case, we're simulating the information universe. And so what you've got here, I don't know if I can everybody, can you see the pointer? Probably not. Each one of those threads, yeah.
Okay, I can move the pointer. Where would you like me to move it? I can, kind of awkward to do this.
On the process thread there.
Okay.
Anyway, this thread here is duplicated 1,000 times, just a bunch of them working together. And the first thing that happens, which I wish I had that damn pointer. Okay, the classifier block is where it tries to come up with a rule that will reduce the chaos in the system. Okay, in other words, they're trying to move the system from chaos to just hydrogen atoms. You can imagine at the beginning of this, the universe, everything is in total chaos. Just a lot of swirly energy, quantum energy. Imagine that. Okay, now these threads are going to try to, they're going to create space. They're going to create a space element, and then they're going to come up with a regulation action to try to move the overall system, which is space, time, to a more ordered, which is, we want to have lots of hydrogen atoms everywhere, and not just total chaos. So the classifier then applies rules to try to change its local state, quantum state, to move in a direction of getting hydrogen atoms. And at the same time, it the next chart you can see is a reward. Okay, what it? Oh shit!
Is it this one? Okay.
Can you put it back?
Yeah. Oh, hang on. There you go. Johnny can see it.
No, you're on slide 6.
Yeah. This is slide 5. And what's going on here?
Okay, well,
hang on.
We're on 7.
There we go. That's 7. So we're on 8 now.
No, you're on 3.
This is 3. It says page 8.
Back up 1. Oh, this is embarrassing.
Well, no
This
stress,
is
guys.
important.
Hang on a second. What? Let's see, hang on.
It's sucking it up.
This it right here?
You had it before.
This one.
I can't control this. I'm screwed.
Are you able to? Trying to do this. This was the one where we're at right now, and I'm going to the
All right,
next.
leave it there.
Okay, we'll leave it there. Okay.
Okay. So anyway, the classifier picks a rule, changes the state, and then the system rewards that decision, rewards or punishes. So if the rule gets you closer to the desired final state, then you get a reward. If you get further away, you get punished. And so over time, okay, thank you. Over time, the rules are being shared among all of the threads. So the entire information universe is growing a rule base in order to turn chaos into hydrogen. And they're sharing their rules basically during this current, what they call a blink. Okay, then once all of the threads have made their decision and come up with their response, then we go to the next phase where they all synchronize and they share rules, and then we go, and then it loops back and we do it again. This model was based on Derek Meyer, who's got a lot of papers out on the information universe. And he proposed this model in a recent paper, which I have referenced in our paper 3 that we've got on ResearchGate. Anyway, so this is his model, and you run this thing, and if you look at the little box down here, you'll see that entropy is dropping. And now another thing this is something that we discovered, which is probably nobody knows, but for this system to work, there has to be a disturbance. Okay. If there's no disturbance, then the rules converge to very simple rules that actually don't work in a chaotic environment. Okay. You have to keep disturbing the system so that it will learn rules that will work, anywhere in the universe. And I don't know, but I don't think very many people knew that or know that. And it is a fundamental discovery on how this could, if this is the way it works, fundamental discovery. Anyway, so let's go on. I've kind of given you. Next slide. Try to get the next slide 8.
Yeah.
Okay. All right. So this is kind of what you would take away from that. All that. During each time element, the agent rule learning is instantaneously shared throughout the information universe to build a shared rule base to regulate the material universe. And the entropy is reduced as unwanted quantum states are eliminated. We saw that. If you run the model, you'll see that. In general, okay, this is really interesting. Now, in general, a network of intelligent agents, in one of our papers, it's a traffic system model. can be a complex adaptive system, CAS, that evolves to greater complexity and has emergent behavior. Now, think about that. This is important. If the information universe is a network of intelligent agents and they communicate and they share rules, they're going to have emergent behavior. And guess, one of the things that, this is just like the human brain. The human brain is a network of intelligent agents and has emergent behavior. And the emergent behavior is consciousness. So it's possible, if this model is right, that information universe is conscious. Not only intelligent, but conscious. Okay. Just an interesting little thing there to think about.
Okay, next slide or?
Okay, next slide. I need to move along here. Okay, this is important, and we later on how our system works. This is the concept of features, and the classifier system. What comes into the system there would be numbers, and they get converted to letters. And you can see that we have features for the conditions and features for the action. And you can see the actions are very small. We either increment or decrement or do nothing. So that the changes that are being made are incremental. And I think this is an important part of the system science here, because you want the system to gradually evolve. You don't want it to make some huge jump, because you know what happens when you do that in a control system. It becomes unstable, right? We don't want to generate instability. The system will never converge if we do that. So anyway, so that's why I set it up this way, and it works fine. Okay, but anyway, these are features. So what comes into this thing is numbers, usually integers, set of integers, and they get converted into letters. So the rules then are symbolic. Feature 1 equals A, then the decision is increment, 1. This is just an initial rule. This is not, the rules look quite different once it learns.
Next slide.
Okay, so there's the features, rules. Okay, let's go to the next chart. I just want to.
Next one. Okay.
It's kind of. We did some research. We have this book called Wave Theory of Information, and this is a model of how to deal with, I think, with the interface between the information universe and the material universe. We think that this might be a way of dealing with it. So basically, when we run this experiment, we're going to get, just like we did with the missile problem, we're going to get a whole bunch of measurements. And these measurements have to be correlated. We have to take out the noise and get a nice clean signal. Clean meaning that the signal actually represents what the disturbance was. In other words, if you can't discriminate what the disturbance was based on the signal, you can't learn anything. So that's real important. And so Amar is going to spend a lot of time talking about that, because that's critical to this whole thing. Okay, then you take a time, it's a time signal, and you do a frequency transform of some kind. And this will produce the coefficients of the frequency. And these coefficients, of course, describe the signal. So basically you'll get what I call an n-dimensional message vector, which describes the signal we're getting from all the measurements. See, this is the same problem I had with the missile. Same problem. Okay, then what we have to do to learn anything, we've got to randomly generate a very large sample of message vectors for a set of disturbances. In other words, we're going to do supervisory learning. We're going to generate a set of sample samples, and then we're going to these messages come right in the middle of what I'm trying to say. Anyway, so we get a very large sample of these things, and then they have to be, in other words, these are signals. Then they have to be clustered, and we have a clustering algorithm that I've developed. And if you can't cluster, you can't learn anything. Okay, so if these samples don't discriminate unambiguously, you can't learn anything. That's a good takeaway. This applies to anything you're trying to do like this. Okay, so we get after we cluster them, we get n-dimensional, I call them exemplar vectors. In other words, the original message vectors are clustered into what I call exemplar vectors. But they're still n-dimensional. Okay. Then the next thing we do is we have to map these. As I said before in our original problem, we had an n-dimensional vector. We have to map it into feature space. Feature space is a curved manifold embedded in the n-dimensional space. Okay. So we use a neural network. It's I call it evolutionary neural network. It's the best way to evolutionary algorithms is the best way to learn anything, any kind of optimization problem. So you run these things through the neural network, and what pops out is your features. Okay, next chart.
Okay.
Chart 12. Need to move along here.
You want me to go to this slide? Or this is
Yeah. No, that's not it.
This was where we were.
Okay.
Yeah.
Right here, okay. Yeah, this is it. Okay, the way this works then is we have to do this iteratively. We've got to learn both the neural network and the rule. So we're going to optimize both the neural network and the rule. So we set the program up so it iteratively runs the exemplar through a neural network, and then it learns the rules, and then it gets a set of rules, and then evaluates the rules according to ambiguity, and we would like to have as few rules as possible. And so it keeps doing that until, you know, it just, this way neural networks work, and evolutionary algorithms. You have, let's say you have 50 examples, 50, you've got 50 neural networks and rule sets. And so let's say 10 of them you keep all the time, you don't change those. And 40 of them you evolve. And so, but we always keep 10 of the best ones. So every time we do this, we sort the best ones up to the top. And this goes on for a while until we eventually get a neural network and a set of rules that unambiguously will discriminate all of those cases. And this happened on the missile problem. We ended up with a neural network and a set of rules, and it could discriminate 100%, never made a mistake. And then we actually ran flight data through the thing, for firings, not simulated data, but real data. And the same thing happened. It was able to discriminate 100% given those rules. So this works. So that's good news, because you might want to apply this to your problem. Okay, next chart. Next chart.
Right here.
Okay.
This is the quadrupole.
Okay, this is the quadrupole experiment. And the idea here is in the middle, we'll have a test material, and we got 4 coil electromagnets around the material. The electronics provides high current signal to the 4 magnets. Okay. And I'll show you what that looks like, because we have a mathematical model of this whole thing. And then the sensors are set up around the test material. And I don't know how many there'll be, but we will bring in signals which then Amar will correlate and do the noise reduction. The computer manages all this, and I'll go through what that does. Let's go ahead. I need to move along here.
Okay, next slide. Okay,
Next part.
this is the next one right here.
Yeah, this is okay. Electronics. So we're the box. The electronics would be some kind of an oscillator and an amplifier, and it'd be able to produce different frequencies, different levels of current, and different waveforms. And I've got a box to do that. And then the input to the thing will be from the computer, telling the box which combination to use. So each combination of power, frequency, and waveform will define a specific disturbance. So that would be that 3 dimensions will define that I call the disturbance space. And looking at the how it's wired up, the four coils are wired so that B1 and B3 are in the same phase, and B2 and B4 are the same phase, and then adjacent coils are out of phase. So what that does is you run a frequency, so many hertz, the field is rotating and twisting. So it should provide a really interesting disturbance, to the material at that center. And next chart.
Okay.
Next chart. Next.
Oh, this one? You want to keep going? This is the
Yeah,
quadrupole. This is the,
This is the good one.
Yeah.
Yeah, this is a Mathematica model of what the field looks like in terms of not the vector, but go back. I forgot to mention.
Here.
Top of the back one.
okay, I just did.
Right, yeah, here. Yeah. Notice you got the vector here. That shows the B vector field. And you notice the different colors have to do with strength, field strength. Okay, go to the next chart. Next chart. Next chart. Thank you. Okay, and you can see here that the field strength, back up one.
There you go.
It's still not, there you go, not touch it. Okay.
Play.
You can see the B field, and you can see that the ones that are across from each other are at the same level, and one's up and one's down, okay. And then this thing rotates. We have an animation in Mathematica that shows it rotating, and you watch it rotating. It's twisting and turning, and you ought to really put a real twist on space. Maybe. I know Evans' work, where he discovered that with the Einstein Cartan definition of what general relativity, that you could have a twist in space-time. Yeah. Anyway, so maybe we'll twist space-time. Okay. Go ahead. We'll go to. I want to move. Next year. Okay, then the sensors, basically, as I said, there'll be some numbers, they'll be sensing different things because we expect different kinds of regulator actions. So we're going to have sensors that pick that up. And then the other thing we'll be interested in is what is the truth? Because we're going to do reinforcement learning, so we need to know the truth. And the truth, of course, would be the 3D vector that identified, what was the disturbance. Okay. So between the signals we're getting from all the sensors and the 3D vector, then we have an n-dimensional vector. And part of it is defining, what the response was. And part of it is what the disturbance was. All that in order to be able to do the learning. Okay, let's go ahead.
Okay.
So next chart. Okay. So the computer is performing 3 tasks. The first task is to get that large n-dimensional training set. And so what you do is you just randomly select disturbances and you run them through there, and you get the signal, disturbance regulator action signal. And you basically save those in the memory, and then you run them all through the clustering algorithm, and then you save those. So then you have basically now you have a training set. The reason you do this is because in data, in data mining, you can have an astronomical number of possible data points. We get 100,000. You run this thing, but the learning algorithm can't handle that. So you've got to cluster them into what I call exemplar vectors. noise. This is a really important point. This is a real important part of the data mining. So if you can't cluster, you can't learn it. So anyway, we end up with this training set. I call them the exemplars, and basically what it is that the original training set will cluster around an area. This book on the wave theory of information talks about that these messages will tend to cluster within a certain region depending on noise. And so we have the same exact problem here. So anyway, by running the clustering algorithm and getting what I call the training set, it's a much smaller number. You have like you'd have 50,000 in the first set, and it might go down to 1,000, which is a manageable number. Okay, next chart. Anyway, this is really important. Wait, next chart.
Yep, that's task 2.
Yeah. Okay, and once you're in task 2, then it's like I said before, you go into learning mode where you take the exemplar training set and you run them one at a time through an evolutionary neural network. So what you do is you evolve a neural network, then you run all of the training set through that neural network and through the rule learning. And then when you're all done, you evaluate the rule set, how good was it at being able to unambiguously identify all the disturbances. And then you go back and you do it again. So you just iterate this until it converges. Let's go to the next chart. Let's go on to the next chart.
That's 3.
Yeah, there we go. Yeah. Okay, so then at this point we've evolved a neural network and we've evolved a rule set. So now what we think we need to do is we think that we have to run a sequence of disturbances against the material in order to unlock the effect we want. In other words, I wouldn't expect it to happen, with one. It might take 10 or 100, in a sequence. So what we're going to do is we're going to use what I call reinforcement learning, which is related to excuse me. It's where you can learn a sequence of rules. You can basically solve a problem. You get a sequence of rules that will lead you from point A to point B. So it's reinforcement learning. And one of the things we'll have to do is we'll have to make sure that if you get an unsafe disturbance, in other words, the temperature starts to increase towards infinity or tries to fly away or, other really weird things, you have to shut it off. Okay, so one of the things the computer will do is if it gets a signal that looks like it's going in the wrong direction, it'll shut it off, and the rules will be evaluated, and they'll get punished. You went somewhere we didn't want to go, so everybody in the rule sequence gets punished. But if you end up somewhere where we did want to go, then all the rules in the sequence get rewarded. And of course, there's things in between. But this is all in my book. This works great, and this will be an important part of the experiment, will be to take the rules that we learn for our disturbance space and see if we can't move the system to where we want. Well, it might be propulsion. Maybe you're trying to get propulsion. Maybe you're trying to get an electromagnetic field. You know, you want a current. Maybe you want to reduce the weight, and you want, you know, whatever it is you're trying to do. The system will basically try to go there. Okay, so I think that about, I'm almost done here, mine.
One more.
Next chart.
Next chart. There we go.
Okay, why don't we skip these? I think we don't need this one.
You want me
So
to
let's go on to your, yeah, go ahead.
That's
Go
now. This
to
is
22.
this is 20.
Yeah, we don't. Yeah, let's skip that one.
You want to discuss this one?
This is one.
Okay.
Skip this one.
And guys, it's Tim. Let me jump in really quick. So we are actually into our Q&A session, but I think it's okay. Let's push on and have Amar do his presentation if that works.
Okay.
John, you mentioned being almost done, or did you have a little bit more that you wanted
This
to
is his.
present?
This is one more slide.
Okay. Okay.
John, you want to
Okay,
do this?
go to your slides. Amar, you're on.
Okay, I'm on. All right.
Amar, you're on.
Okay, I'm on. I'm on. Okay. Can everybody hear me? Yeah.
Yeah.
Good.
You sound great.
Okay, terrific. I'm gonna take my coat off because I'm getting hot.
Okay.
Okay, so
before you start, should I mute John out, or should he be on still?
John, do you want to stay on?
I mean,
I think it'd be okay to have John on there.
okay.
If he wants
Okay.
to be. Yeah, that way if he wants to interject, he can.
Just in case.
Okay.
I might want to interject something.
So I'm going to try to I'm going to try to do is try to bring this back to what John is saying, but from something that everybody can kind of relate to. Okay. First of all, we're trying to get at the what part, not the how. John has been trying to tell me that, and I'm telling him. We both tell each other this thing, but it's the what that we're after. And what is sort of a hard thing to do, because some of our a fellow I have a great admiration for is Dr. Richard Feynman, who always said we don't even know what energy is, or what force is, or for that matter, some of the basic things. We know how it does things, but we don't know what it is. So we are really after the what part, and I'll kind of build a framework. I'm going to try to see if I can build a framework around this. And okay, I see things popping on my screen here. So hang on just a second. So anyway, this part of the work involves my software, and I've been working since '93, and I've had some interesting things happen over time. I had a stint at NASA at Jet Propulsion Lab. I was a principal investigator in '98 and 97, 98. It wasn't directly involving my project, but it was a test I wanted to do on the Cray J90, and I ran a test there to see if I was going to get some kind of interesting results. So anyway, ultimately, that was out of the way, and then I continued on with my work and see if I can. It was like a what do you call it? A litmus test for certain things I was after, and then I continued on, and then I found myself developing a software that would do these three things. Well, what I'm covering is called I call it the AUP, or the Autonomous Universal Predictor, which is in this box that you see. It's a section of the software application. Well, okay, so basically it's the part that involves me interfacing with the sensor data. Okay, it's there where you need to be able to separate the noise from the signal. Okay, and what I'm doing is not like your standard filters that are that are used in many applications. What I'm doing is something that is quantum, and I'm going to get into that in a moment. Let me see if I can. So what I'm going to cover in the next few slides is going to be these three parts: the feature collector, the lab view spectrum, which is an ancillary process, and then this cross correlation across the sensors. Okay, so I'm going to go to the next slide. Okay, so it says here that the quadrupole operates, this is the feature collector portion. The quadrupole operates like a magnetic resonance imaging, an MRI, on a wafer or a disk. So if you think about it, what we got here is an MRI, a magnetic resonance imaging in a sense. But what we're doing is, instead of putting a human body in there, we got a lump of material. Well, it's not a lump of material. It's a substrate where it could be something that's highly electropositive, and then you got something out on the as a conductor that's highly electronegative. Okay, and then in between you could have something that's like a gate. Okay, but the point behind here is that we're matching the frequency to the material, whereas most folks are trying to match the material to the frequency, and it's far more difficult to do it that way than the way we're approaching it. This allows us to work with all kinds of materials, and in a way, see if we can test out this hypothesis which is very well motivated, that there in fact could be a IU, or an information universe. Okay, and I'm going to try to show you how that connects with something that's already in a way being done, and we did an experiment at UCI in 2006. I'll explain that in a moment. So the sensors collect signals measuring changes in the material properties. We got here thermal, gravitational, electric, magnetic, from the IU signal source. Okay, so as John mentioned earlier, that we're looking for anything interesting. Okay, and normally, well, not normally, what you want to see is you want to be able to observe something. So that was why I mentioned earlier that the substrate should be having something that it wants, or something it wants to give, excuse me, and the conductor could be having something that it wants. So there has to be already some kind of a dipole in place. Some folks would call it, like Tom would call it, Tom was a close friend of mine, like John. In fact, John Searle, Tom, and I would actually have three-way, moment. I'd be the John, and we'd get on the phone and be talking with Tom. And this was a frequent. We were actually, Dr. Clymer, we were all working on a effort to look at John's project in a different light. And anyway, it was an independent thing, and it's kind of resulted in this, that what we're doing. I won't get into that at the moment because it's easy to divert attention to that. What we found out is Tom would say, well, you got to have broken symmetry. He keeps saying. Well, what he's saying is that you better have some kind of a dipole so that you can see something, observe something. That's the goal here. And so we don't know what we want to make sure is we have to make sure that we have a way to regulate, disturb, regulate, and control. And that means this is a dynamic phenomena. Okay, this is highly nonlinear dynamic phenomena. So you are in a quantum soup. Okay, and in another thing, I'm focusing on that section on the sensors collecting signals. What we're saying here is that these quantum particles are having a conversation. I'm trying to remember the physicist at Caltech who said this. It's excellent YouTube if you could find it. They're having a little conversation. What you don't want to do is you don't want to zap them with noise. What you want to do is sneak up on them and eavesdrop and see what they're talking about. Anyway, that's the kind of idea here. And I'll get into that. So it says here, many sensors and signals can vary for each, which means we're talking about changes that can take place on the wafer, everywhere. We're talking about a wafer, but it could be a disk, okay? What that means is that we can have, you can imagine that the disk is representing the XY axis and that the sensors are on the Z axis, okay? And they're not necessarily, it's a non-invasive approach, right? So they're not necessarily in contact with the disk. So they could be, a distance away, but not necessarily in direct contact. So this is a way to non-invasively get the signal despite any noise distortion. And by the way, noise in a situation like this, which is dynamic, is pretty much anywhere. You can't say that there's one optimum location for a sensor. These sensors could be picking up noise anywhere. And so we have to be able to separate that noise from the signal. Now, it says here, goes on here, signal features, entropies, are swiftly collected and compared, contrasted across the sensors. Okay, so what that is, and I'm going to try to see if I can see what that is this. Okay, what I'm doing is I'm taking I'm taking these signals that are coming in, and I'm getting a measure of their entropy. But what I'm doing that is different than what you'd be doing in the standard modeling usually involves linearization of things. Okay, and it also requires that you have to it operates in a classical sense. I'm not operating classical. I'm operating quantum, which means that, and I know that then it's gonna be kind of difficult to understand this if you're not used to the quantum stuff. But imagine this: you got to be able to visualize. I like to make things simple. I want to make it so that everyone can understand what's going on here. Imagine flipping a penny. Okay, if you're flipping a penny, it's when the penny is flipping. That's when you want to know what's going on. You don't want to know what its state is when it's finally landed. I'm not interested in that. I'm interested in the state space of the flipping penny. Okay, so imagine zeros and ones flipping around, spinning up and down. Okay, you can call them the spins, you can call them what you want to call them, but they're flipping. Imagine these ones and zeros are flipping. They're superpositioning. Okay, they're overlapping each other. That's our quantum world. And what that means is that you want to know the entropy state space of that flipping itself. Okay, so I don't let those things land. I'm not in the world of classical. I'm in the world of quantum. Okay, so what I'm doing, when I say I'm getting entropies and they're swiftly collected, I'm talking about entropies of the state space of these things flipping around. Okay, so then these are compared and contrasted across the sensors. Okay, next slide. So here I'm telling myself the next slide. I'm actually in control. Okay, so here we go. We got sweep one. So what happens is that I'm concerned about two things. I'm concerned about precision and I'm concerned about accuracy. Okay, so I have a system that is autonomously doing the data mining of the sweeps. Okay, excuse me, of the measurements. Well, what I'm doing is when I'm taking measurements, let's say this, so this represents the first 100 increments. Okay, how would I explain this in few words? Maybe I might not be able to do this in a simple way, but what it is that imagine that you have 100 qubits. Yeah, imagine 100 qubits. Okay, 100 qubits. So what I'm doing is I'm getting a measure of the amount of entropy treasured in the qubit individually as this is happening. Okay, and in there I'm going to find out that some of them are excuse me, some of them are tending to be negentropic, or negative entropic. Okay, and then some of them are being entropic. So in this, the blue lines represent negative entropic. Red lines represents positive entropic. Okay, so that means entropy is towards disorder. Negative entropy is towards some kind of a dynamical structure. Okay, it's all dynamical. Okay, now this, you can look at the first 100 qubits as an aggregate. Okay, now one measure is not good enough for me. So what I do is I take multiple measures like that. Now this is just 3 attempts. I can take 1,000 of these attempts. Okay, and I'm just talking about the first 100. Okay, you can represent that in terms of some kind of a squiggly. We call it a squiggly, like some kind of a disturbance. Whether we are inputting it into the system. But I'm particularly interested in the system's feedback, because what we're inputting into the system, we already know what we're inputting. What we're interested in, what's the system's feedback. So I'm catching this. Now the precision has to do with how many times I'm sampling in generating these measures, but the accuracy has to do with how well my measures are. So imagine. So I got to give you an example, an analogy. I don't like to beat analogies to death, but you got to see an analogy here. So in a case like this, you got to think in terms of where you're signing your name. Okay. Imagine your signature, the signing of your name is sort of like an aggregate. Okay. Okay. Now, if you sign your name again, it's not going to be exactly the same signature you had before. It's going to be slightly different. Okay. And so what we're doing here is we're trying to show that there's some kind of stochastic behavior taking place in this 100 qubits. Okay. Okay. Now, just kind of bear with me. If there's something that's not quite making sense, it's okay. We can discuss in the Q&A if time permits. So we go on. So what I did is I also said that if there is a researcher involved in something like this, they may want to see an ancillary step so they can visually see what's going on. Okay. It's easy on the eyes. So what I did is I talked to some folks at LabVIEW in 2005, 2006. I say, hey, gentlemen, can you help me out? Can you create a subroutine for me? Because I was working on I didn't get any kind of special grant. What I was doing is I was working from with very little. So I tried to get, what I could. And then they did a little subroutine for me. And what I did is I generated my data. I piped it to an Excel spreadsheet, and then they sent that, and I sent that through the LabVIEW subroutine. And what LabVIEW did, LabVIEW National Instruments, so it generated color hues. You can see here, dark fringes were the entropies. Well, dark fringes are the penumbras, which we call them umbras, and the penumbras are the illumination and shades. Okay, so you can see what that means is that it'd be really easy on the eyes if you were to see something in a timestamp. And going on to the next section, to the next bullet there, it's umbras correspond featured entropies, and penumbras correspond featured negative entropies, negentropies. Okay, what that did is it led me to UCI. So I was scouting around. I didn't know where to go. I started saying, well, I need to find somebody who really, really has a need for something like this, because this is an unusual case. So I said, I got hold of a gentleman, UC Irvine. I can mention his name if you like, but it's right now. I just want to cut through all this and get to the key things. We sign a non-disclosure. There's certain things I can't disclose, but what I did is, what I'm going to share with you is what I did. So it was a fMRI imaging, and what they were doing, they were working with EEG, electroencephalogram. And what an EEG does, let me just stay on this slide for a moment. EEG, what you got is you got a person, and on their head, they have topically all these sensors on their head. It's non-invasive. And what they're trying to do is they're trying to collect the, a person's tapping their fingers, for example. Or they might be looking at something. They might be doing calculus. I don't know. They might be doing something cerebral. That's the idea here. And what you're doing essentially is you're sending an input into a neural system, okay? And this you can imagine to be the IU, the information universe, okay? And this comes back to Dirk's work that Dr. Clymer, John mentioned earlier. What is happening here was that a person could be tapping their finger, and so they have. He gave me 8 sensors, and he said, okay, of the 8 sensors, I want you to tell me whether any of these sensors are they able to cluster, kind of the way John is saying. You're saying the same thing. Can we find a correlation between these guys? Because then we were learning something, right? Anyway, what happened was I went ahead. I took his hexadecimal data. That's how I was given. It was given to me in terms of hexadecimal. And what I did is I took, for example, for sensor 3, I took the hexadecimal data and I converted to my measures. Now again, remember, these are measures of entropy in a quantum world, and I know this, and it's going to be a little bit tough to kind of, maybe for those who are not used to the quantum, it's going to be kind of difficult to explain that in a few words, but I'll try to see if I can, get across to you in subsequent slides. So I don't know if you can see this. It's going to be hard for me to, and if I can, let me see if I can bring it out. So if you can see these numbers, you can notice that the numbers are not that different. They're not that far apart. In a sense, it's kind of like what John was saying earlier, that I'm not making radical moves. My moves are just like that, an increment up, increment down, somewhere in the middle. What I'm doing is I'm trying to get a way of honing in on some particular kind of particular kind of change, and see if that change is telling me anything about a degree of entropy or degree of negative entropy. Okay, these are entropy measurements, okay, between 0 and 1 that are treasured in each qubit, okay? So you can see this doesn't really change much, and it can get very precise depending on how, very accurate and precise. Now, precision has to do with how many times I'm running it, okay, as I showed you in the earlier plots, okay? Now, let me zoom back out of this. It may be, okay, so what I did next is this. If I can move to the next slide, hang on. What's going on? Bear with me. Let me see what's holding me up here. Escape there. I got it. Okay, so what I did is, if you see this right here, you see that arrow that you have there, that black arrow in the black box. Now, if you go to this slide, you see that on the bottom right here, you see that rectangular black box. It's the same thing. It's just been compressed. So you can see what that data sample right there really represents, just that little small slice down there. That tells you how much data I was generating from the information he gave me. Now, let me explain something here. He's giving it to me in static mode. I'm not interested in, ideally what you want something dynamic. This software is suited, it serves its true purpose. It serves its true purpose in a dynamic situation. In other words, we don't want to be getting this thing after everything is done. We want to be doing it while it's happening, okay? So that's what my software is actually suited for. In other words, it's designed for a dynamic phenomena. So when that person's tapping, I should be already getting all the stuff I want while it's happening, okay? So I'm getting these measures. Ultimately, that's where I wanted what I can do. This was actually already datafied in raw data, okay? And it was not cleaned. It was raw data, just the way it is, okay? And they call it blind source signal separation, okay? Anyway, so these lighter hues that you see represent the penumbras, and any dark hues you see is representing the umbras, okay? So the penumbras tells me that something interesting is going on, some kind of a dynamical structure, and the dark hues represent the entropies. It's the noise that's getting in. Now these strips it's not that you got a bunch of strips here. What you got is really one single strip. It starts from letter U. I labeled this, and if you can see the letters there, and it starts from letter U and it ends at letter W, okay? Now, if that's hard to see, what I did is I created an inversion, and there's your inversion. So this is sensor 3 inverted. So you can see that it goes from V to W. So this is one long strip, okay? I just happen to be looking at that one section of the strip just for your, just to show you the connection between that and the measurements I'm generating, okay? So it really starts from V, ends at W, okay? But imagine this thing going on dynamically ad infinitum. I'd be just there taking measures, okay? And I'd be creating these umbras and penumbras for the experimenter. The machine doesn't need to know this. The machine can just directly input the measurements, and then from there we go, okay? But I'm getting these things, and so all of what happened then is, so this is the this were all the slide sensors that I had 1 through 8, UCI, and these were our piped Excel, and then I ran the NI lab subroutine, researcher. So this was a sensor 1. And okay, and by the way, the top portion you see, that you see the miscellaneous register data, that was what we call registered junk data. That's sitting there. And it's this is because I didn't have a lot of things. I was not well equipped. I had what I had, shoestring budget. So I'm working with what I got. So I had to kind of, I had to kind of do a lot of things manually. But really what you want to do is you want a data that is not without any register. When you have a registry, if you're familiar with programming, in a register, you're going to have a lot of junk ones and zeros if you're not completely using it. And I wanted to make sure I got rid of that. So that's why I'm also creating these inversions. So again, sensor 1, this is a piped version. This is the actual one that I showed to the researcher. And you have to, again, look at this as one long strip. Don't look at it as a bunch of strips. It's just one continuous strip. It starts at letter V at the top, and it ends at letter W on the bottom. And then here's sensor 2, okay, piped. And then here's this inversion. Here's sensor 3 again that I just showed you earlier, piped. And then this is the actual inversion, the way I wanted to present it to the researcher. Likewise, 4 piped. 4 was in it. Now this is happening very fast. I'm not sitting there and computing anything. I'm literally going in there and getting measures, okay? And I'm not data dredging, I'm data mining. Because when I do the aggregates that I mentioned earlier in that black plot, the plot with the black background, I'm getting a correlation, which I didn't get into detail. That correlation allows me to ensures me that my measures are mined, not dredged. Okay, so I can get into more details on that, but that's something I can get into later. Okay, so this way he's getting true measures. Again, sensor 5 piped, and then again here it is with the inversion. Sensor 6 piped, inversion. Sensor 7 piped, inversion. Sensor 8 piped. This happened very fast, and I generated the results. And then what I did, I don't have this with me here. What I did is I actually cut these things in with a scissor, okay? Because I didn't have I didn't have all the ideal resources. What I did is, and then I actually stitched it together so that way it would be like one large panel of strips. So you can see sensor 1, 2, 3, 4, 5, 6, 7, 8, 9. And when I showed it to the researcher at UCI, he was able to look at this in timestamps and say, oh, it's interesting. I can see that sensor 8 correlates with sensor 6 at timestamp, whatever. He would break it. He would take it into so many sections. And you say, well, that section right there correlates with what's happening here. And he would see that sensor 4 is correlating with maybe sensor 2 right here. So he'd see different correlations, saying, when that person was tapping his finger, oh, something is happening in this part of the brain. Now, this is a very, very difficult problem to this day, right now, as I speak, in what's called multivariate neuroscience. It's a very, very complicated problem because they're dealing with what's the source problem. The source problem that they call is a problem that really affects all of science, everything in science. The source problem that they call in the neuroscience is basically this unknown origin of where this stuff is coming from in terms of signals that we don't know how to separate. I mean, you can't apply, first of all, you can't be thinking classical, but furthermore, they're not only in classical mode, they're thinking linear. So that really is that's even an additional handicap. So first of all, you got to stop thinking linear, and then you got to stop thinking classical, and you got to work in the quantum. And you don't have time to compute. You got to go in there and get the measures. And that's what I'm doing. It took me a while to do this. Okay, I mean, to come up with this stuff. Just like John's been working on his research, I've been working on mine since '93. Then this goes on here. So now I'm kind of speeding up here a bit. Let me see if I can. So cross correlation across sensors. Use timestamps, as I mentioned earlier. Visual ancillary spectrum, segmentation, AUP, OpEMCSS in tandem. So while I'm doing this, the ancillary stuff is for my visual. But OpEMCSS can just strictly start taking this stuff in and then start classifying. No limits on sensor quantity while sensors position and target wafer or disk location. So naturally, we want these things in areas where we're not going to get, we want to focus on areas where we really are interested in. And of course, I can get into the physics of this, but I don't want to get into it at the moment. I want to kind of stick to the experimental stuff and kind of tie it back to what John is saying earlier about, the need to make sure that things are clustering, okay? That otherwise, if we don't cluster, we can't learn. What I'm demonstrating here right now is I can cluster and I can find things that are correlating. This is a big problem. And anyway, now let's see. No limits on sensor quantity. Well, yeah, in general, because when you're in the world of quantum, right? When you're working with things in the quantum, you are pretty much, you're going to cut through a lot of stuff, okay, that normally you couldn't if you're in a classical world. Okay, so UCI fMRI researcher noticed immediate cross correlation by a visual cue. As I mentioned earlier, he saw right away, oh, that's something we didn't catch, it's there, okay? Sensors need to be in contact with wafer or disks, need not be, okay? But topical and non-invasive to materials. AUP bridges quantum to classical. It could be microchip, yes. My software can be put into a chip format, okay? So this is an interesting, now what is different from what I'm doing versus what's going on in the quantum world right now, including the folks at Google and again, I respect everyone's work and what they do, so I'm not telling anyone anything. All I'm saying here is I'm just saying that I'm doing something different than what the other folks are doing, in the sense that I'm not particularly interested in computation of any kind. I'm not particularly concerned with a special gate. I'm not trying to hack anything. What I'm trying to do is I'm trying to understand the quantum world and the information that's treasured there, okay? And there are certain things they'll tell you that you'll never get the complete information of the treasured, that's treasured in a quantum bit. You'll get something partial. And that's true. I can relate to that because we are trying to, as I said earlier, we're trying to sneak up on these guys and try to eavesdrop on their conversation. And what that's an analogy to saying is that we're trying to find out exactly what is their state space. What exactly is, you can't quite zero in on it because noise is always going to try to distort it. But the way to keep noise at a bay, if you will, and this is sort of in the wave theory of information, where they're saying that the limits have not been reached yet because we're only scratching the surface. We need to come up with better ways to engineer and do system science to get there. Ultimately, what that means is that you want to have a way of knowing at least something about the state space of that quantum, the amount of information that's treasured in a quantum bit, but it could be partial, which is fine. But you want to do it in a way so it's direct. You're not computing anything. You're directly getting in there and finding out what's going on, because we don't have time. If this system goes into meltdown, we don't have time for that kind of stuff. We got to jump in and do something right away. I think there is a latency for the system to, to do anything. So in a way that affords us time to do certain additional things that we need to do to, improve our controlled system, so that we can get more rewards and we can continue to reward the system more rather than punish it. So that's important. Let's see, next slide here, and I'm kind of getting close to the end, so I don't want to take too much time here. So I said, okay, we can also use, since John's software was used at a graduate level for a master's program and higher, I presume, and I've used mine in a research at an advanced research level. It can be used to pursue R&D, and I by the way, just so you know about my background, yeah, I have a bachelor's in electronics technology, but I specialize a great deal in independent study and information theory for a long time, and then I pursuing a degree and finishing up a degree in mathematics, an accelerated degree, and then I'm planning to go for a graduate program. But I didn't want to do that until I had something that I could actually create a framework around that interested me, that can also also, I think, help bridge a gap between the mainstream science and what we're talking about here, which is what I would call extreme science. That it's not there's nothing wrong with it. It's just that it needs some kind of a framework, a knowledge framework for the folks in the mainstream to kind of wrap their head around. And I could talk about Caltech another time, but that's another discussion. But John and I had an interesting, very positive feedback. Now the next thing is, at first, if I was to do I did the hard part already. My main concern here is I need to do the formal work. But in effect, from what I've done from '93 to present with a stint at NASA and then some other work I've been doing, first, my dissertation's already kind of in place. My first part would include what I just talked about. Okay, and then the second part would be covering my research collaboration with JPL. A little stint there with some tests I did, and then what I did with UCI, which I covered today at APEC. And the third part would cover some other work I've done. I was involved with LENR, low energy nuclear reactions at Cal Poly, with Dr. Robert T. Bush and I think it was Bob Eagleton. And that is an interesting research involving the work of Pons and Fleischmann that had took place a few years prior. And there was a frenzy. Anyway, that's what I want to say, is that there, and of course I had also interaction with some other folks, including John and Tom. And then what we're doing now is kind of what it's led to. And we can discuss more of that. The business model, dollars and cents, I put that in quotes, cents. Intellectual property, defensive publishing, trade secrets, circumventing, not infringe, patents involving claims, specifically admixtures with synergistic effects or materials matching frequency. Okay, so I felt that it's important that I also have a business model. So for those of us who are engaged in this type of effort, that we have some direction. And it actually led me to write a letter. By the way, I'm very neutral when it comes to who's our president. I don't, whoever is our president, I always respect whoever's in office. So I've corresponded with President Obama, and I've also I had to correspond with President Obama on Star Trek initiative, and I also interacted with President Trump on another topic that's also on the extreme ends of things, and this involving science. Okay, and that's not directly related to this. That's why I'm not going to get into it at this moment. It does have tie-ins, but not directly to what we're talking about right now. Anyway, but why I brought it up is because defensive publishing, trade secrets, process is hard to figure out. File for patent, but nice. We're dealing with a tech that does seem to have the best of both worlds, and I have to say it that way and frame it that way. It's the best of both worlds in making our humanity great again, and at the same time also help protect our country. Okay, because it does have, naturally it's going to have defense applications. So we have to find a way to show that there is a best of both worlds. One way to do it is to have a way to keep the technology I'm trying to put this in a business framework that where the certain information is kept proprietary for obvious reasons, while you can still do research and development that can benefit the consumer, that can benefit all of us. Okay, we the people. Okay, but it can also have that other added benefit to make sure that we are also for national security reasons. When you say that, sometimes people get the wrong idea, but often you have to find this balance when it comes to certain kinds of technologies. And there I have John Searle, myself, Tom Bearden. I'm sure I know that the three of us we felt that way. There's this sort of a balancing effect. Go ahead. So this, what it does is it affords us to continue R&D at high to mid low TRL, tech readiness level. They use the TRL acronym at NASA. Low TRL is akin to NIDS, National Institute for Discovery Science. Yes, let you know that in the 90s, late 90s, right after it was a hiatus. So what based on the work of NIDS, I had a chance to speak to Kelleher, who's involved with NIDS, and some of the work that was interesting. I'll keep it in that ballpark, involving Robert Bigelow. And let's see what else. I was also in touch with Peter Sturrock at Stanford. And actually, and the reason I'm bringing that up is because I sent Peter Sturrock, Dr. Sturrock, a message saying that at the Pocantico conference that you folks had in '97, this was 2000 when I sent him the email. Said, was there any discussion? And then this is in quotes. Was there any discussion involving the use of intelligent sensors for detecting any physical patterns in real time? And I was referring to that interesting work that was done by Robert Bigelow and NIDS investigation, on the ranch, the ranch episode. Okay, it's a difficult topic, and I don't want to get into it too much. That's why we call it low TRL. Okay, so it kind of allows you to continue to do research in that area while you still have spin-off technology. So there could be stuff that we can do now that could have immediate rewards and still do mid to low TRL. Okay, we're aware of the admixture material science, patents claiming synergistic effects involving materials matching frequency. Well, there are many of them, right? I think there are quite a few out there that are saying that, look, if we get this kind of material lined up with this, provided they can get 1 + 1 = 5, then they're getting something more than what they expected. Then they got a patent of some kind. We're not in any way infringing that. What we are doing is, what our goal here is to build a toolbox. And the toolbox would allow us to test different kinds of materials. And the way I described earlier, having certain something that you can observe, like a dipole effect, for example. But what we're doing is we're matching the frequency to any material. Okay, that way we're not infringing any of these folks. So this is sort of an interesting business model in the event if someone wanted to pursue this. This is a model that I'm kind of building around so that it can actually establish small business innovation research for continued efforts in this kind of extreme science. And with getting the help of our, getting the backing from our federal agencies and our, because the main thing here is that we want to make sure that technology like this is in the right hands, and it's also something that can help benefit, make humanity be a better place, because we certainly could use a technology that can get us, advance us further. Okay. And of course, I left it at this with the Richard Feynman at the end. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And I think Sean Carroll is trying to do the same at Caltech. So this is the summary of the presentation. If John wants to jump in. John, you're there? No, okay. I'll just say it. So the summary of the presentation, the takeaway, is to understand the intelligent adaptive agent concept applied to control IU, disturbance regulation, understand operation of information universe regulation in the material universe, understand why quadrupole experiment is critical to safe research in IU regulation. So IU is, again, that information universe. Did I rush through a little bit too fast? Yes? No?
No,
well, you did good.
Huh?
I guess we got a little time for questions and answers.
Yeah. Let me do this, guys. Let me do this. Let me mute you both out really fast. And then, sorry about that. So what I want to do is I'm going to put it on speaker mode, and everybody, please, you know what, here, I'm going to stop screen sharing. Oops. Yeah. Stop sharing. There we go. Sorry about that. I'm going to put it on screen share mode. Everybody, could you put your hands together and give Amar and John both an enormous hand? Gentlemen, thank you very, very much. That was a ton to work through. And it was actually, it was very different than a lot of the stuff that we've covered here. So we do have a few minutes here. I will ask you to unmute, and then John as well. Okay. So I guess the question, let me start with the questions here then. The first one would be, you've talked about the information universe several times, and I'd just like to clarify for the audience. So you told me the other day that this is different than Bohm's holographic universe. The information universe is kind of another, like a string brain type dimension that can basically controls the rules that drive the material universe, right? Is that the way you're describing it?
John, you responded to, so I'm going to let you speak.
I didn't hear all that.
I'm just wondering
Sorry,
if there's, I'm sorry, is there kind of a layman's description of the information universe? I'm trying to connect this back to things that are a little bit more tangible for kind of the average person.
Well, yeah, I think that Dirk Meyer had it in his paper. Basically, it's just a whole bunch of threads that are regulating different 3D elements, and they're all communicating and sharing their rule learning, and they essentially he called them blinks. Time goes along in blinks, which would be time is also discrete. So you have during the blank, there's no time, and you fix it, you regulate everything, and then they synchronize time up throughout the universe, and then they go have another blank, and then I thought that was a pretty simple model. That's what my little model does.
Oh, okay. Well, and then from a propulsion aspect of this, if I could ask a little bit about that also, have you found any insights? And this might go to Amar, because again,
Okay.
Amar, I know you've worked with Searle and Bearden. Have you found any insights that might help from the propulsion aspect?
Absolutely. Well, yeah, I don't want to, here's what, we actually had a talk with John Fry, Fry Electronics. It was in 2017, because he came down, he was curious about what we were doing too. And so he gets into some deep philosophical discussions with us. It was at Cal State Dominguez Hills, and in the math department. I can document that. I think so, at least. I hope so. But no, we were there, and anyway, frequently what happens and when these discussions come up, especially these extreme topics, is that, well, heck, where does this energy come from? I mean, we talk about this, and I was struggling with that too. And I said, Richard Feynman said, I like Feynman and I like the way he thinks. And he said, look, we don't even know what energy is. And he's right. We don't know what it is. We know how it works, but we don't know what it is. We don't know what force is. Well, then I started thinking, I said, well, Tom, John Searle, and I, when we would talk, one thing Tom would keep talking about is this energy that's trying to hemorrhage into our three space. He would say that there's a four-dimensional energy that's trying to hemorrhage into our three space, and he'd say that, well, this energy is compressed by c squared, and I understand what he's getting at, and of course, what he's saying is that time is a very real thing. I mean, I'm talking in terms of Minkowski's ICT. It's a very real thing that it's not an illusion. It's real. Except he talks about time polarized photons. Okay, I don't want to get too deep into this because it could get hairy, but that's okay. I want to stay focused on your question. Well, what I was asking myself is, well, maybe as Dr. Clymer, as John said earlier, and I really resonate with this. And Dirk's talking about this too. Smolin gets into it. He says, where's the qualia? Qualia. Qualia. how do we fit into all this in this qualia? Because it seems, and there are papers published on this, where rigorous papers, they're saying that when you try to get into the world of energy, even when you start studying certain subtle things in energy, you run into problems in mathematics. They call them inconsistencies. Okay, and a fellow mathematician, well, I mean, a fellow mathematician of Einstein. Well, let me frame it again. Let me rephrase this. And a mathematician who was well involved, very much involved with Albert Einstein, and I think Hilbert, maybe Hilbert. Anyway, he was the Kurt Gödel had put together a theorem. He was able to show that, look, mathematics itself is inconsistent in certain cases. Well, it turns out now there's some papers that are being published. They're saying, look, we can't even. It seems that there is a lot of this going on even in the field of energy itself. Just the study of energy in itself, there are things in it that are intractable to the extent where it leads into these paradoxes. Now, what that's saying is that it's almost as if it's axiomatic in the sense that it was already there. How it got there, we have no idea. What is it? We have no idea. It's as if there's, in other words, you can't wrap it around with mathematics. It's almost as if math takes a back seat when it comes to this stuff. So what I'm trying to lead up to is this, is that it could very well be that the information universe is what is basically giving is as Dr. Clymer and I discussed this, is that it has to test itself out. So it has to find some kind of an optimal way of going about doing it to see if certain things work. In order to test it out, it has to have a place to test. So it creates an exhaust, if you will. That's you can call it space-time. And in this exhaust, the part which is where the information universe and the material universe are actually adjoining is this hemorrhage that that Tom Bearden is talking about, this structured energy in the time ICT. But we don't observe it because it is happening at a very, very fast pace, high speed. And also, what we are detecting is the stuff that we can observe, not the things that we are, not how it's interacting. We don't know how to since we don't observe it, we don't see its we can see its effects in things that are far from thermodynamic equilibrium. But that is if we are willing to actually pay a close attention to it. For example, us being human beings, we are ourselves far from equilibrium. And what our brain is capable of doing, what our heart, everything, what we're doing as a whole, as a system, is so complex that it appears to be being regulated by this IU. But how is it doing it? It could be what is adjoining it is this structured information in the time ICT. And so so to get back to the propulsion part, is that what we're trying to see is, considering that we may not be able to wrap the math around some of this stuff because it may be that it's just there, then the question is, how do we tap into it and use the information universe? In other words, do the precursor engineering in the information universe to create the effects here. So this is kind of getting into the realm of, we're talking about an emergent phenomena. And it's this is sort of at the crossroads of at the edge of knowledge right now. So it almost sounds fantastic, but it certainly solves some of our major problems that we're having right now. And anyway, I'll leave it at that. I don't know if that answers part of your question. Go ahead.
Right. Let me add something. The Dirk Meyer papers, most of them have to do with how the human brain interacts with the information universe. And this goes along with what I call the quantum brain theory. And those of us that are familiar with neural networks know there's no hell that our human brain could do what it does based on just the neural network that's up there. That the idea is that the neural network is actually a function of quantum states and probably connected to the information universe and makes use of the information universe and in some way to greatly expand the capability of the brain, you know, to be entertain a vast, you know, vastly increased number of behaviors than would be possible with just the neural network that's there. Neural networks are very brittle, so this thing's got to be changing as a function of quantum state. And anyway, Jerk's got a paper out where he talks about that. Several actually. It's quite compelling, actually, the idea. It's like the information universe is speaking to us all the time. You know, we just listen.
Yeah.
Maybe that's where a lot of insights come from. Yeah.
Well,
I know that sounds crazy, but I think it's true.
Maybe jump in on that. Just a quick thing.
Sure. You know, but before you jump in though, let me ask, because we have 27 people in the conference, 25 other folks. There's Will. So after you go, Will Reichen had a question. So yeah, go for it, Amir.
Yeah, you know, there's another thing. I just recommended John a book, and he just ordered it. I was going back and studying Minkowski's he gave a topic. He gave a talk. I think it was in 1908 at Cologne, Germany, and Minkowski gave a talk on his math that was, of course, building on the Minkowski framework geometry. And I gotta tell you, what he was really saying, I think, was I don't know how to say this in the way I want to say it, but it seems that as if it may have been something may have been overlooked, that we need to go back and look at listen to what he, read his actual presentation, listen to what he said. It seems that because of his mathematical insight, as I understand it, Einstein did not quite catch it the first time around, and then he started realizing he had a need for it when he got to GR. But when I read this material on Minkowski, I think it's from Minkowski Research Institute, I was able to see that there was a lot of things that Minkowski did not get credit for, and he should have been given credit. And I think it also turns out that if he may have been misunderstood, because he was tending to be more in the mathematical realm. And I'll tell you, let me get to the punchline. Let me get to the key points behind it. What he's really saying is that your space-time and my space-time are personal. And I recall another gentleman saying something like that. I can't quote it, but I do recall him saying personal, was Kip Thorne at Caltech. That your space-time and my space-time are personal. So your world line and my world line are different. So if you look at that as a system science, a system as a brain, the brain has all kinds of things going on all the time dynamically. So it has its own space-time world lines. So if we really go back and look at the physics that Minkowski was trying to get across and really understand the way he was presenting it, I think we'd see a lot of things that perhaps might help shed more light in special relativity and the general relativity that may have been perhaps missed. I'm trying to say this in a nice way, because I have no disrespect for anybody. Try to like this as much as I can about this.
Okay, well, let me do this. Thank you. Let me go to Will Reichen. And again, I should apologize. We're running low on time, so I want to try and get Will in. Will? Sir?
Okay. Okay. So, as someone who is a computer scientist and who has spent many years in evolutionary systems and neural networks, I feel that your data sets are too small. It's very difficult to know which neural network you're using as you don't identify the category. And each neural network method also has different ways of handling the data sets. So, and then the other thing I would like to say is that evolutionary neural networks are even more difficult than standard neural networks, neither one even approaching the level of the human brain. So my question on that is, do you plan to expand your data set and in order to get more finer resolution for what you've already done? And then I would like to make a statement, and that is that because you brought up the photon. If you were standing in the blackest, darkest room in the universe, and you had the right type of vision, then a single photon has enough energy to light up the darkest room in the universe. So bright that you can make out all the features in the room as if it's broad daylight. So I'll just make that statement because that place does exist. I just can't see anything about it.
Okay, and so I think Will's question. Thank you, Will. I think his question was: are you looking at expanding the data set to be able to get finer resolution with the neural network results?
Okay, well, can I answer that? No,
Sure.
then what Amar can answer. Okay, well, what I'm doing is when we generate a training set, we would generate all possible combinations of our frequencies, energy levels, and waveform. Well, you know, it might be 100,000 different ones, and when we run it through the neural network, well, basically we're trying to learn the mapping to go from the n-dimensional space to the feature space, which is embedded in it. It's a closed manifold that's embedded in it. So that's all the neural network is doing. It's just learning that mapping. And the way you know you got the right mapping is when the rules work. It's very simple, really.
I understand.
And
The training,
as big as you think it is.
Oh, okay. Oh, I may have thrown Will off. I was.
I'm sorry. I didn't realize that sorry, I made a mistake. I didn't realize I actually had the mic on.
Oh, okay. Okay. Yeah, well, so I think. Oh, and I was responding in chat to Will's thing.
I mean, that can be as large as.
Need me to jump?
Okay, well, Will is asking about the size of the training set. And he's right. You can't be infinite. You're going to have to set boundaries on, you know, what disturbances you're going to be experimenting with. And you can make that as big or small as you want. And probably end up doing it many different until you find the right I would call space, training space, you know. But then all you're doing is mapping that training space into the feature space using an evolutionary neural network, which means that evolutionary algorithms are being used to do the mapping. So it just keeps, you know, generating population after population until it produces what you want. So, and it's all it's doing. It's just mapping from the raw data into the feature space. The feature space is what does the discrimination. So the raw data is a lot more data than tells you anything. So you map that into the feature space, which basically does the discrimination. That's all there is to it. And we use evolutionary algorithms to do the optimization. So
I could jump in.
yeah.
So
Yeah.
I can work. I can make it as precise and accurate as required by the, depending on what we need to do. And of course, this thing is autonomous. It continues to explore. It's unsupervised. It continues to explore on its own within that precision and accuracy. Also, it's in a deterministic. It's deterministic. It's in a deterministic framework. In other words, it's learning just like John's program is learning, but it does not rely on any a priori. It doesn't care about a priori. A priori meaning that there's some kind of a distribution beforehand. No, it could be anything. It's going to try to learn, and it's going to try to find out what it is. In effect, it's like getting a. I don't like analogies, but it's like getting an image of a example, and you're trying to get this. If you put a penny under a piece of paper and you scratch it, if you scratch it coarsely, you're going to get certain things. If you scratch it finer, you're going to get more things. But in this case, we don't even know what we're looking at. So what I'm doing is I'm finding out what these things are, and they're dynamic. So this is hard to describe, and even analogies are not that good. But it's that kind of a thing.
Could I interject something here?
Well,
I think there might be a confusion between a large feature space involving a very large number of different disturbances versus what Amar does, where he takes data from one disturbance and tries to extract the information that discriminates that one. So it's two different things going on, and both of them are critical to solving the problem.
Yeah.
So,
Guys-
so I guess really what I want to
That
ask
makes
then
sense.
is how different are you then from NMR? I mean, NMR does almost the same thing, doesn't it?
Oh. No, because go ahead. Who's,
Um,
do you want me
like
to?
I said, I'm trying, but I have to take what Amar gives me as the truth about that disturbance, individual disturbance. He's going to tell me, he's going to give me information that will uniquely discriminate that disturbance. And then that goes into the database with all the other disturbances. And then I try to cluster and classify all those disturbances and map it into a feature space.
Yeah.
John's
and
So,
software.
guys, let me actually. I think we probably need to move on. So, let me do this. Let me mute you both out. We could probably come back to this in Q&A if you're both with us still then. But let me do a mute all. Okay, and let me see. I'm gonna go to gallery view, and again, everyone, please give Amar and John an enormous hand. Thank you very much. So next, we want to go to Falcon Space. I want to talk to Mark. Mark, are you with us still? I'm not sure. He's with us. I'm not sure where he is. There's Mark. I'm going to step away for a minute. I'm going to call him real quick. Okay, sorry about that, guys. Mark is actually, he will be back in about 2 minutes. He's in another place right now. Do you guys want to do some more Q&A? I think Gravity Alchemist had a question. So Amar, are you and John okay doing a little bit more Q&A? Sorry, you're.
Sorry, I just unmuted.
Okay, let me get Gravity Alchemist then. Sir?
Okay. Hi. Hey, I just want to say this has been a great presentation, and I want to thank you for your security concerns for our country and the technologies that you're working with. They're all over my head. I do have opinions, though, as everybody knows in the group, because I'm not a classically trained engineer scientist, but I have an aptitude for science. I like Richard Feynman, and you've mentioned him a couple of times. I like some of those guys. I like Jim Gates. I think he talks a lot about some of the things that you were talking about. But anyway, do you think there'll ever be a time where we can go to the internet and run simulations like you guys are doing with this software? Or is that just something that's never going to happen?
I don't see why it can't be done in a simulation form. I don't see what the limits are there. There's some things I got to keep quiet for obvious reasons. But I don't see why. I think that we could. John. Actually, I can answer it this way. LabVIEW is the same way. LabVIEW has certain proprietary things in place. So you can't. You can still run it, but you're not. You don't know all the specifics of what's going on. But and John's software is the same way too. So we could create a shell that would allow folks to have access and they can test and they can see what's going on. I mean, in fact, John's program, even right now, the way it's set up is it's what's the term we use in computer science? It's escaping me. A heuristic. You want a heuristic. You want to be able to literally plug in, because I'm the same way. I like to understand what's going on. I just don't want to. I mean, knowing is one thing. Understanding is a whole another ballgame. So I like to be able to apply myself and understand what's going on. So yeah, I'm 100% with you. I'm sure it can be done. And when someone wants to get something, there's also ways in which you can have an executable. So you can still run something, but not necessarily have all the details, and that's for security reasons.
Okay. Hey, one last question. One last question. Okay, so one of us comes up with a great idea, and we might think, well, that propulsion system might have a national security interest. So at that point, do like the men in black jackets show up and say, hey, we're taking your ideas off the internet and you're going private? How does that happen? Do you know?
I could tell you how that happens if you want to know.
I do.
Yeah. Okay. Sure. I better take my coat off again. I'm getting hot again. Yeah. No. I'll tell you how that happens. I can kind of pick up on it, these things, because I've dealt with this kind of stuff in a way. But anytime you generate a very low frequency, because this kind of thing would. Tom Bearden. Tom was a very close friend of mine. I mean, I knew his family, and we talk. I call him anytime. And one thing I remember is that he said that yeah, it's in his books too, but it's the concept. I build and design things in my, so I'm not relying on one source. But he mentioned something about time reversal zones, and I don't want to get into the details of that right now. But what I will say is that from what I found out is that your frequency starts getting smaller. It gets tiny and low frequency. So if you create an ELF, you're going to get picked. It's going to get picked up on somebody's system. They're monitoring for that kind of stuff. So yeah, if you're you see, that's why you got, you want to make sure look, it's safety. I mean, we got to understand that, I can understand their position. So naturally you don't want to be doing that kind of thing anyways, but that's why you want to make sure you got, I'm trying to say it in a way so that it's we the people, because it is we the people. We're the ones in charge. That's what our founding fathers were all about, and I support that. I don't want to get political here, but I mean I do support this. But we the people also have to be we the responsible people.
Yes, Amar,
I hope I answered it the best way.
Yeah, you have answered
Absolutely.
my question. Thank you.
Okay,
Yeah.
well, thank you again. Let me go. Okay, now let me go to Mark. And again, Amar, thank you. And I should apologize for jumping around.
Oh, okay. I also should
Okay.
apologize. I was out of the room at that time. So there's not that many updates from the lab. We're still waiting on the 3D printer that we need for the Alzafon experiment to finish up the tuned resonance chamber where the sample is going to be held. We did get in this sample of this metal over here, which I'll show you my hand. This, for those of you who don't know, it's slightly bluish. This is osmium. And we're going to make a gravitator out of that. T.T. Brown in his patent mentioned that the heavier the material used, the stronger the effect, and osmium is the densest metal. So why not just go for broke and shoot it with osmium? Another thing we were talking about, me and Jeremiah, was that we don't actually have a warp drive detector in the lab or a laser interferometer table. Which is, the go-to way to detect these kind of fields. So we wanted to set up a laser interferometer or the warp drive detector or the UFO detector, whatever you want to call it. The problem is that most of these tables are made out of metal, and a lot of the experiments involve high voltage, so we couldn't use that. So we did some searching around, found the stiffest plastic composite we can find, and it's sitting right here next to me. This stuff can hold 45,000 pounds per square inch or something like that without deforming. Has extremely stiff plastic that arrived here at the lab on Friday. And we're going to set up some laser pointers and stuff on it, and we'll have carry handles on it so we could just move it around to any experiment and see if there was any effect that we didn't notice. And we'll have to try some of the older experiments too, because there might have been something there that we didn't notice. Another setup that we're going to have on this board is a wavelength detector. So we're going to have I think he recommended the neon laser or something like that, or the helium laser that has a very steady frequency output, very clean, steady frequency output. And then you have a frequency detector on the other side, so we can check if there was any change in frequency, and we have the laser output coming from inside wherever we expect the field would be. So if there's any change in frequency, then we'd know that there was an expansion or contraction of space-time in that space. Again, like I've said many times in the past, I'm not convinced that warp drive even exists, but this would be the way to detect it to the best of our ability. What else do we have going on in the lab? We got a new vacuum pump over there that came in from San Diego. I still need to get the connectors for it. And that's just for general lab work. And well, hope to have some actual experimental updates in 2 weeks from now. We're going to get the printer in on Monday or Tuesday, and we're going to use that to print the inside of the tuned cavity for the Alzafon experiment. For those who don't know, Alzafon is basically a way of creating a coherent matter state where you orient all the subatomic particles along the same spinning axes, and that should theoretically make the craft weightless along its spinning axis. And as Einstein said, nothing can go faster than the speed of light. Well, that also means that if you get if you make the craft weigh nothing, it can go faster than the speed of light. So how do we make it nothing? Dynamic nuclear orientation, according to Alzafan, should do the trick. And that is something that we're working on. Also, I have behind me a massive, right over here, this is a massive electromagnet. Weighs about a ton, and it's on caster wheels, so we can move it around. Here's the power supply for it. And behind it over there, you can't really see it, is the Klystron. That's the microwave energy source, and over here is the Klystron power supply and the signal generator and the signal analyzer, and also the forward and aft power meter using a cross guide. So that's what's going on in the lab. Not much. There was a couple experiments that we did over the last 2 weeks, mostly with Jeremiah and Wayne Ojala out in Canada, and Namtran in Vietnam was doing some experiments as well. There's also another interesting update. There's a new member of the Falcon space team. His name is Charlie, and he's a PhD electrical engineer working on the Alexei Cherkov gravity flyer device. And this is something that we've been a little skeptical about. Some people think it's a fraud, that he's a fraud. Alexei's videos of his spinning device is fraudulent and doesn't really work. And some people think there's something to it. But I'm kind of on the fence on that. But if anyone is willing to do the work and actually build a device, I'm totally game and totally helping them, because that's the only way you can find out. Alexei's not really responding much to our inquiries, and he keeps on pushing us to look at Grabinikov, at Hutchinson and Searle, and like, I don't really know where that goes. There was another guy on Facebook who was working on this device, and he apparently got, this was very obscure, we didn't hear about it until recently, and he apparently got 80 grams of weight loss in his testing device. And unfortunately, he passed away recently from a heart attack or cause unknown, and he was working on the device at the time. We're in contact with his widow about getting that device and setting it up here in the lab inside of our Faraday cage, so that we can replicate his work and continue it on. I think his name is Chris Hartman or something like that. We'll look into that, and if we get that device down here in the lab, we'll definitely turn it on and replicate as best we can. Look into all his notes and try to continue where he left off. There's a good reason why there is a heart start defibrillator here in the lab, because a lot of these experiments are very dangerous. So that's just a reminder to anyone out there who wants to work on this stuff. You should have a lab partner, and you should have a defibrillator on hand, for dealing with the high voltage components. And yeah, it's pretty much what's been going on. Any questions?
Awesome. Well, I have a question. Now, when you mentioned the laser interferometer, for me, that's exciting. And I think Sonny White had mentioned this too, right, over at NASA. And the idea is, hey, maybe we are modifying gravity. Maybe we're modifying time space. And there's sorry, Jeremy Reese is trying to butt in. I was teasing him in chat. So maybe we are doing these things. How do we know? How do we measure it, right? If you guys are able to get that, it would be not only would it be amazing to measure your experiments, it would be very interesting to take stuff like electric motors, electric light bulbs, God knows what, anything that's lying around the lab, right? Maybe common devices are modifying time space a little bit. I've never seen anyone do real testing on that. Who knows?
And also, all laser interferometer tables that you can find commercially are made out of metal, which would interfere with all these experiments, which is why we needed to go with plastic. This is a plastic composite, so it has a pretty high, dielectric strength. But it's the stiffest stuff we can find, and I think it's even better than the aluminum tables that they have offered. With its stiffness, it's 2 feet by 3 feet. It should be more than big enough to move around the lab, put it on any experiment, stick it on top of the Tesla coil, whatever you want to do. It's not going to interfere with the experiment. It's not going to interact with it, but it will give us results that we can quantify and say, we tried this experiment. We also put the warp drive detector on it and saw this, saw that, whatever.
If I could jump in real quick, Mark, as I recall, in discussion or in chat, or we have so many channels, so I don't remember where this was, but I think there was a talk about remote, because right now the table, that's kind of up close, but wasn't somebody talking about some kind of a remote distortion detector also, right? And I'm thinking about UAPs here. You need to have something that you could point at a UAP or point at a light in the sky and say, something's going on there.
No, I'm not really familiar with
Okay.
UAP detector. No.
Yeah, I don't know. I know that there is the proton magnometer. I believe that was one of the things. But Will has his hand up. Will, go for it, sir.
Yeah. Sorry, how large is the model you want to 3D print?
It's not just the size of it; it's the accuracy, and they're quite small components. But we need a 3D printer here in the lab in order to modify it, because you never design it correctly the first time. Yeah.
Yeah. Well, I have 2 industrial 3D printers right here in my room.
Where were you located?
Japan.
Yeah, I have a 3D printer in the other room. I actually got into 3D printing like 7 or 8 years ago with the Solid Doodle 1 and 2. That company's out of business already. And then I got the cheap Chinese CDC one. This new printer that's coming in should have an accuracy of up to 10 microns, which is extremely accurate. And it's like a custom small company that builds these highly rigid ones. So we're really excited about that. I actually use 3D printers to build equipment for the hybrid battery shop. So there's, I've been
Raise 3D and Epsilon W50.
Yeah, I'm pretty much going to be printing. I think we're going to be printing ABA plastic, which has a very high dielectric strength. We're going to be printing like these squares or rectangle shapes, and we're going to use those to shape the waveguide chamber and see if it's in resonance or not. And if it's not in resonance, all you can do is print another one or cut it down and make it smaller. It's all you can do.
ABA or ABS?
ABA.
ABA.
ABS is a common plastic. This is not a common plastic.
Yeah, I don't have that on my list. So I'll have to take a look at that.
It has a very high melting temperature of like, I think it's like 250 degrees centigrade or something like that, or 270 for the nozzle temp. It's a very high nozzle temp.
Right. Okay. I'll look into ABA. That's interesting. Always good to learn about something new. Also, if you guys happen to be interested in vacuum chambers that can cut out the Earth's magnetic field, I have a couple extra ones.
So yeah, we'd be very interested in that.
Something I can work out with you on that. We can talk about that later.
Yeah, it's made out of mu metal, or
it has mu metal lining.
Really cool. Yeah, how big are they?
One of them is 2 meters across internally. And
wow.
And the other one is about, I think, 30 centimeters.
Well, 2 meters across internally, that's large enough to run a lot of experiments in. Is that round? Is it a ball, sphere, cylinder?
It's a cylinder, yeah.
Wow.
It has a lot of ports. So
that's
okay. Will, do you have Mark's contact info?
You can respond to the email.
So
you could just respond to the email invite that goes right to me.
Okay. Yeah. That email that goes out, that will come back to Mark. Okay. Well, so do you want to go to open discussion session now? Or
if anyone has any more questions, or you want to discuss any of this stuff further.
Okay, let's do that. Yeah, no, I think it's kind of a light day today, right? But it's the day before Easter, so and I guess it's Judeo-Christian holiday. I guess everybody has.
I think Ron has a question.
Oh,
Ron,
does he?
Yes. Hey, Ron. Come on.
Where's
you gotta unmute yourself, Ron.
Let me find her on.
Put the glasses on. Yeah, put on your warp drives. Technically, glasses, according to some interpretations, glasses are warp drives because they curve,
Okay, no,
right?
no, different thing. I heard it gives you a 10-point appearance on your IQ. So I need it. I need a 10-point uplift on my IQ. So yeah. The thing is, I see you have elemental osmium.
Yes.
You have elemental?
Yeah, it's pure. It's the metallic version. We plan on melting it inside of a vacuum chamber using induction heating. Actually, that was something else.
You're duplicating Brown. Brown used, as you know, litharge. He used litharge, which is lead oxide. So do you plan on taking that to it? I'm not sure how easily osmium is to oxidize. It looks as though it might be difficult. Do you plan to?
No, it's actually very reactive with oxygen. When you warm it up, it grabs 4 oxygen atoms, making osmium quatrooxide, which is extremely poisonous and deadly.
Oh God, yeah, and that's why. But like I said, because Brown used lead oxide is not really that great either, but probably not as bad.
No, osmium quatrooxide is extremely dangerous. Which is why we're going to have to melt these into plates inside of the vacuum chamber so that it doesn't come in contact with any air. We're going to use, what do you call it? We're going to use induction heating system that we set up in order to warm it up. And then we're going to have ceramic plates to withstand the heat. It takes 3,000 degrees centigrade to melt.
Yeah. It's getting toasty.
Very hot and toasty, yeah. But inside a vacuum chamber, it's not so bad because there's nowhere for the heat to go.
Yeah, another item on Chekhov. I'm friends with Alexander Frolov, and I always ask Frolov about Chekhov, but I don't know. Frolov has said negative things about him, but sometimes they're competitors.
Yeah.
Because there's something called
we had Frolov in the chat group at one point, and he gave us this design for an experiment we called Frolov's hat.
Yeah.
And it didn't work, but he's a very colorful character, to say the least.
Well, also, if you look on YouTube, there is, I'm not sure what nationality. He might be Taiwanese, Chinese, but there is a reverse engineering of the Chekhov device, and the guy goes through it component by component for 2 hours. Have you ever seen that?
Send me the link. I might have seen it, but send me the link. Yeah, definitely.
He spends 2 hours on it, going through each individual component that he sees there. What worries me is why they use such a large air gap and neodymium. To some degree, why do you use large air gaps? But anyhow, okay, I'll beam it to you. And also, I sent to Tim the Silpho Moore and its involvement with the University of Manchester. It's really interesting. I had 4 pages I sent to Dr. Frank Mead, and the page that I want the most somehow disappeared. But the 3 pages there are metallurgical. And like I said, it's Manchester University and their Ferris laboratory analyzed these materials, and why it never got to public. So, okay, thanks again, Mark. Be careful.
Will do. Thank you, Ron.
Okay. Well, yeah, I mean, I think that's pretty much it. I guess it's good time for open discussion. If anybody wants to jump in, if anybody has anything to share, if anyone has updates or anything along those lines.
Yeah, I want to say something. That video, I saw that video about a year back. It's by a Singaporean, and he spent a lot of hours trying to figure out what the circuit actually does. But his conclusion was that it was basically a lifter. And that didn't make sense with me.
That doesn't make any sense. There's no way something that heavy can be a lifter.
Yeah. So he was coming from it from a predetermined outcome.
Yeah, I mean, I think the only 2 options for Alexei Cherkov devices, either it's some magic that he doesn't understand and we don't understand, or he's just holding it up by a string.
You know,
Oh, go ahead.
I'm sorry. I don't want to be negative, but I've reached out to him. Benjamin, you may have as well, but I've reached out to him. I reached out to him once myself, and then I talked with Mark when he did. And in both cases, Alexei redirected back to Western. He redirected me back to other folks. And then I think he told Mark about Tom Bearden and stuff like that. And so my takeaway there was he wants to do magic on YouTube, but he probably doesn't want serious attention, I guess. Now, that was my opinion. It's just an opinion, but
yeah, when the group I was talking to, I was leaning towards believing him, and so I sat down and started deconstructing what he was doing. But then we had one of our members was a Russian guy who used to live in Russia, and he and a few other people did not believe that he was right. But I said, let's give him the benefit of the doubt and try and bring him in and let's talk to him. But he was very reluctant to do that. So we had to drop it at that.
And he also offered to sell you a model, right? How'd that go?
No, he didn't.
Oh, no, that was me. He offered to. Well, I offered to buy one from him. So it's not that he was trying. I don't want to make him seem profiteering. I offered to buy one from him last year, and I said, "How much would you sell me a working?" And I also what I said was, I don't want to steal your idea. I said I would put this up online. You know, I said you would benefit from this both ways, and I'd be happy to pay you for it. And he said that he would sell me one for, I think it was 2,000 euros, but he guaranteed me in the email that without his expertise, it would never work. And that was where I dropped it, you know. So.
Yeah. Apparently there's a lot of fiddling that goes on with the dials, and there's no working theory that explains why it would work. So like, you know, where to even start? He has 2 Tesla coils that are that are working in harmony with each other, and then there's a high voltage field, then there's spinning disks, and then there's ultrasonic transducer on the top of it, and then it all has to be tuned to what? There's way too many devices there to tune. Like even the spinning disks, you have so many options. How many RPM? Is it spinning up? Is it slowing down? Like what is going on? There's so many things. And
actually, if you were at my presentation, I explained because they are both his and Podklanov's device are both related, and both of them I understand trace it back to Nazi Bell experiments, but there is a working theory, and you shouldn't need high voltage. You need about 800 to 1,200 RPMs. It's all there in the presentation, on March 20th presentation. And there's a formula on how to calculate what effect you get.
Yeah, but still the biggest problem I see in all of these is you don't even know what materials that they construct things out of. And there's a lot of conjecture on the Bell, and depending upon who you read, depends on which materials you get to use. So, yeah, until you actually know the materials, I think it's going to be very difficult to figure out a lot of the issues that people want to know. The other problem on like there's people who say, well, I've got pieces of something and it's an alien artifact, but in every case that I've looked at, there's nothing alien about anything that anybody's ever showed. So if anybody has any pieces that they say are truly alien or whatever, well, my lab has more than enough technology to check out any material that you can think that you think might exist.
how would you know if it's alien or not?
Well, that's a good question, isn't it? So, but when you look at the in material science, which is what I do now, we have lots of databases of materials that we can scan for. So anything that you would think would be alien probably wouldn't be in that database, would it?
No, probably would. Why wouldn't it be in the database?
Well, you know, if I remember right, and this was intriguing, Mark, you might have said this. Somebody told me this. They were talking about measuring the isotope ratios. That was supposedly how you could tell if it was alien.
And
Well, that would tell you if it came from a different supernova.
I have a question. You were talking about a system that had a whole bunch of different settings that you had to figure out, right? And like what speed, you know.
That was the electric Cherenkov gravity flyer device. Yeah.
Yeah, that. Why couldn't you use our software to figure it out? In one of those combinations.
Well, if I could jump in, John, John, if you guys had something like that, Mark could probably use that for a variety of experiments. And I understand, I forgot the name of it, but basically you let it run parameters and it comes up with the optimal parameter set for any one of
John, if you guys can write software that if you can write software that can control a rheostat and in order to change our power output for the electromagnet, and at the same time monitor the magnetic field strength so that it knows that it's going up by X amount of Gauss, and then at the same time measure the weight on a sample and graph it all out, that will be very useful for the Alzaphon experiment. You think you can do that?
Oh yeah,
You probably,
but I mean,
probably need like program
that would
and
be basically sensors. Yeah.
yeah, it would be a software hardware combination.
Yeah, and that was
what we're
Jump in. Is it okay if I jump in?
yeah.
Go ahead, Amar.
I talked to Alzaphon and just kind of wanted to side note that his father's book has a section in it that has to do with these distributions, and I think in our paper too we talk about that. Remember, John, the paper from Russia, the Russian physicist, the Russian scientist.
Oh yeah, that's right.
And anyway, that it turns, I mentioned to Alzaphon, I said that your dad, in his book, and there's a particular page, he's talking about something like that, and I wanted to mention that, just so you know, because that kind of reflects our second paper. That is cycles. Sorry.
Is this the book you're talking about?
Yeah, is that the Alzaphon book? Yeah.
Well, this this is the paper that was written by the dad.
Yeah, and then there's a I think, I don't know, it's page 126. It's one there somewhere he's talking about the distribution. I don't know, maybe we can't look for it now, but probably in there.
Oh, you're probably talking about the book that was written by his son.
Oh yeah, that's it. That's the book. Yeah.
Yeah, this was not written by Frederick. This was written by David.
Oh,
David on page 121.
and David actually has come to
read
several.
that too.
David has come to several of our conferences as well.
I'm connected with a few of these guys. Yeah, I know it's in the book. Well, I brought it up just because I think it's I think it's 126. I don't remember now, but it has to do with a distribution and some kind of a distribution, and it has to do with something similar to what we were talking about. It's going to be a long shot right now. I can't. Sorry to do this to you.
A distribution of what?
It's like a I don't know if it's a normal distribution, but it has something to do with things that are not, that like they're cycling. We show that in our paper too. So you have humps.
Oh, right, that.
Yeah.
Yeah, we
I think
figured
it's
out
in his.
what it was. Yeah, what was happening is that there was regulation going on, and it was eliminating behaviors that, and what happens when you do that is that you get, it takes things out of your database, and you don't get a smooth curve anymore. You get something with bumps in it. We did an experiment in our paper too, and that basically is what happened. We had the system set up. It was regulating the control of traffic network, and when you looked at the statistics, they were all bumpy, you know, because a lot of the behaviors that are ineffective were removed from happening. Yeah.
I can't say I understood any of that, but
Our paper too, we talked about that.
I'd have to go, because I sent David a message. Hang on, I'm gonna close this. I sent David a message about that, and I said, you're about the page, and now I have to go back and look at the message. And in there, I recall.
are you talking about these type of plots?
Yeah, what does it say on the top? Does it say anything?
No, they look Gaussian, but they've got bumps in them.
It has to be
Yeah.
Gaussian with bumps, yeah.
I don't know what you're talking about.
Yeah.
I'd have to find that page. But anyway, the point is that he was saying something about if we understood more about this, something along those lines. And I don't remember specifically. But
Amar, would you be able to make the software for that device that I talked about? You probably need like a Raspberry Pi or a Arduino style device that can connect with both the power supply to control the amount of power going into the electromagnet, and also measure the Gauss coming out of the electromagnet, and then step that slowly up and measure for weight loss in a sample. Can you build something like that?
no, I'm not in the position to do so. I
Okay,
can't.
so what
do
is
it.
your software actually good for then?
My software is specifically good for, as I mentioned earlier, it has to do with understanding the quantum processes. So trying to separate the signal from the noise, and that's very important. If you don't know if you can't do that, then you run into trouble, and you can't. It's a quantum thing. So
But we could run the experiment. We can play with the power, which adjusts the Gauss and the coils. That's one of the things we can do to change the disturbance. Matter of fact, we could be searching for, what is the optimal amount of what's the optimal B field to get whatever it is we're trying to get. Yeah, that's all part of what we're doing.
Okay.
Yeah, I would imagine that, I mean, you might have to tweak the software a little bit, but I would imagine that something like that, especially with like recursive neural networks, basically you just tell it what you want to find and it just runs simulations until it finds it, Now, it might not get you all the way there, but it might save a lot of time and effort. That was one of the reasons that I thought it would be great to have Amar and John on, was because they're doing modeling for stuff that's outside of standard science.
So the problem with the model, though, is that whatever you put in, that's what you get out. So if you put dunk in, you get dunk out.
Oh, that's what I do. I'm looking for things that you don't know what is there, and the underlying model does not exist. But I'm going to be I'll be straight out with everyone here. I'm not a software developer. I'm a mathematics is my discipline. And that'd be kind of strange, but software itself is a very specialized discipline. So the things I developed was a mathematical algorithm that was developed by a coder, but I'm gonna have to upgrade it to what to what John is doing, which is right now in progress, work in progress. That's what happens when you're on a shoestring budget. You're not getting funding or anything of sorts, and you have to work with what you got.
So, just considering the statement that you just made.
Yeah.
When we did background scattering on radar signals off of waves, So, we use nonlinear mathematics to solve for those scattering issues. Aren't you using a form of nonlinear mathematics?
Yes, it's seamless to nonlinear things. Kind of being a bit, well, I can get into details, but I'm trying to keep it simple right now. It's not,
Right.
it's a bit, yeah, I mean, I can reference a paper if you like, but it's not going to do any good. I mean, it is look, let me put it like this. It lives in nonlinear. It doesn't have anything to do with linear at all. So
Right.
that helps
Okay.
answer your question.
That's fine. Thank you.
Yeah.
Anyone else have any questions?
I was
Oh, Ron
we
Keto.
know when our stuff works.
Go ahead, Ron.
Am I here? Am I live?
Yes, you're live.
Okay, the name of the person who has the Alexei Chekarov device who died, was his name Chris Hardiman?
Yes.
Well, Chris Hardiman worked with microwaves. He has a tripod microwave device. Have you ever seen that?
No, but I got a lot more excited now.
Yeah, he has it's in his garage. It was 6 foot tall. The bottom is an equilateral triangle at the corner of this 3 foot. I'm going to use approximate dimensions. The bottom is probably 4 foot by 4 foot by 4 foot equilateral triangle. On each corner is a large ball. On the top is another triangle. I think it's equilateral, and it's also what it is. It's at the top they have a magnetron. There's a magnetron at the top. If you type in Chris Hardiman and you type in microwaves propulsion, I'll tell you what, I'll find it. But it's Chris Hardiman. He's been around for years and he is good. Chris Hardiman is great stuff. I may have been in contact with him. He could be my age. I don't know how old he is, but his microwave experiment supposedly. Oh, I think it may also have been linked to Jean-Louis Naudin laboratories. But I'll send you the thing for the Chris Hardiman propulsion device.
We're in contact with his widow about getting all the equipment, actually.
Yeah, because I've seen some of his stuff. I looked at some of his stuff, and I go, oh my God, we probably were in contact 30 years ago, back in the 90s.
He's been doing this for a while. I mean, if that's the case, we'll probably expect a lot of equipment. I might actually, have somebody fly out there to go look over everything and help pack it up.
Yeah, because what he does, I'm impressed by him. What I want to do, I'll dig it up and I'll send everybody on the list. Also, I send something out. Yeah, I send out the Silpho Moore saucer thing, but I'll send out a new one, and I'll send out the one on Chris Hardiman and the tripod magnetron. It's I don't know what effect it is, but it's microwaves. He saw something. It was big, and it was unshielded. I think it just sits there out in the open.
Oh, well, maybe that's why he had his heart attack.
Yeah, I'm saying. Okay, well, I'll beam you some stuff. So I think I'm going to go into my email now. So nice meeting everybody and great presentations. Take care.
Happy Easter.
Thanks, Tim. Thanks, Mark.
Bye, Ron. Yeah, what a small community. Everyone knows him. It's a real shame when people like this, pass on because of simple mistakes that they've made without protecting themselves. So we have here at the lab a room size, it's like a 6 foot square Faraday cage of where we do most of the experiments. Hopefully his device would fit in there, so we'll be able to protect ourselves from it. But from flying saucer accounts, people who've gotten close to them have gotten burns and radiation sickness and all that kind of stuff. So just like you're building a jet engine, you don't want to stick your hand inside the blades while it's turning. There's inherent danger to any form of propulsion. You just got to understand it and protect yourself from it adequately. That's what we plan on doing.
I was going to ask John. John, could John's software right now, the way it stands, could it be of any use? John, what do you think? Could the OpEMCSS by itself? I mean, for the things they need, they may not need what I got.
We got to have what you got because we're doing quantum fields, and they're very, we have to somehow untangle that. Where the problem I had with the missile, we didn't have a problem. I mean, we were able to measure things and map directly into the feature space. There wasn't any problem with that at all. I didn't have anything like what you got to solve that problem. I would imagine most problems are like the missile problem, where the measurements are clean and there's very little noise involved, and we can take care of the noise with clustering. So yeah.
Will, did you have something to say?
Me? Oh, well, based on your comment about the UFOs, I thought the coolest comment was the Nazi Bell scientist that got to melt like plants in front of their toy. So I just thought I'd throw that out there.
They melted plants?
They melted like plants, according to the book Nazi Bell. Yeah, I thought that was pretty cool. So, and after a while, they put on some type of rubber suit to somehow protect them. So it's in the book Nazi Bell, originally written in German, but translated in English. So, yeah, but as you said, it's a good tale on safety first. In my lab, everything is safety first. So, as you said, there's never a single person left in the laboratory for any reason. So, I have to always have two people. So
well, when you're running experiments, for sure, yeah.
I worked in a radiation lab, so I would know, because I as I mentioned earlier in the presentation, I worked with in the LENR, low energy nuclear reactions at Cal Poly. So you got to know where the heck you're walking in the lab. Sometimes you might be shooting beta rays. Don't walk through that place. So
Look at my
happened.
My
I actually almost happened, and the guy literally screamed, and he was teaching a class and says, "No." Yeah, you wouldn't notice that, but it's that type of thing. You wouldn't notice it, and you got to be careful. Yeah. So.
Yeah, I use XRD and NMR and all these type of devices. Also a lot of high voltage stuff. So totally agree. And always have a badge. If you're going to work with anything that can potentially generate X-rays, you have to have a badge. And there's various procedures for using those badges. And it's very important to generate monthly reports on each person who has a badge. Because if you go over the limit, you could potentially hurt them.
Yeah, we had a badge.
Yeah, I have a little keychain over here that from Nuke Alert would actually it can detect X-rays and gamma rays, and it like makes a chirping sound whenever it goes up the radiation levels. So and we also have lots of detectors in this lab. There's an oxygen sensor because we do have liquid nitrogen in here, and the liquid nitrogen replaces the oxygen in the air. We have that's basically a vacuum pump that pulls air out of the lab, so we can move that around to any part of the lab that will be making noxious smoke. We have a range of detectors for all different frequencies and lots of radiation stuff. Yeah, there's a lot of detection equipment here in the lab, and alarms can go off and stuff like that.
Yeah, do you have ozone detectors? I mean, you did say you work with high voltages. High voltages generate both X-rays and anything over 15,000 volts. Actually, maybe
You can make ozone with lower than that. We have a
anything
great
over
ozone
15,000
detector.
volts is dangerous. So,
Okay, we have a great ozone detector. It's called our nasal passages. Ozone is very easily detected by its smell, and very familiar with that smell. But yeah, ozone is it's an irritant, and at high levels it can really cause some damage. But you can smell it at that point because it has a very strong smell. The danger is the things that you can't smell.
yeah. So, anyway, just be careful about your high voltage use. So,
Oh yeah, yeah. We have a 1 megavolt Marx generator here too, that we have a pull string for. It can make a 4-foot spark, and it's 7 feet tall. So we only run that when it's in like the center of the room, and not in this room. We have another room back there where we can run that for different experiments. It's basically simulating lightning.
did you build that?
It was mostly Jeremiah's work. I helped him a bit with the soldering, but yeah, we put together off of these panels that we got from, like, I think it was X-ray equipment. So it's like a whole bunch of 30,000 volt capacitors, and there's 2 capacitors per stage for a total of 960,000 volts. So we call it the megavolt Marx generator.
Sounds pretty cool. It's good that you made it yourself. It's a good learning experience.
Oh yeah, I mean, we built a lot of the stuff ourselves because they don't exactly have laser interferometer tables at Home Depot.
So that's true. That's true.
Yeah, but they do have PVC plastic, which is a very, very good dielectric material, and that's what we use as the scaffold for the Marx generator. And for a lot of the other equipment, we made it out of the PVC plastic stuff, which is awesome to work with.
Yeah, and as you mentioned that, where did you get your ABA filament? Because I've been looking online and I can't find it anywhere.
I got it from Amazon. Let me make sure that it was ABA. It's not like a standard plastic that you normally use.
There is ABA, but it's only used in blow-in plastics, as far as I can see. I couldn't find any filaments at all.
Just give me a second. I'll find it for you. Should be some here somewhere. Oh, ASA. I'm sorry, I got that wrong. ASA.
ASA. Okay.
ASA as in snake. Apple, snake, apple.
Acrylic is a styrene. I see.
Yeah, this has from my research, it has the highest dielectric strength of any 3D printable material.
Really? That's very interesting.
It also has a very high melting temperature. So you need to get your power supply and your all that stuff need to be ready for extreme heat. I think it's like 250 degrees centigrade.
I think,
Yeah, 240 to 270 degrees centigrade is the range that it needs. Very high temperature.
oh, I'm over 300 on these two, so that's fine. So
Yeah, good.
cool. So always good to find a new plastic because you never know what they can do. And I do a lot of cryogenics, so always looking for something that can deep freeze. So
I don't know if ASA can deep freeze, but that's a good thing to mention. Do you know any plastic that can hold liquid nitrogen without cracking?
I use ABS for that.
ABS can hold liquid nitrogen, right?
Very nicely.
It's good to know because we've had problems with our last experiment holding the liquid nitrogen for the doer, and because we used PVC for it and just started leaking.
Oh, that was shatter. So that was shatter. Yeah, I would say I didn't use liquid nitrogen for a door. However, I mean ABS for a door, but I do use ABS for the fittings in my superconducting experiments, because we design superconducting materials. So yes.
Okay, very cool. Anyone else? It's been a pretty slow day here at APEC. I think Easter and all that has has everyone gone to hanging out with family and whatnot.
Yeah, I think it's kind of slowed things down a bit, you know. I was really excited though. I mean, you know, and so I absolutely promise, swear to God, I will fix the Roger video. And I will also install that plugin too. As soon as we stop recording, I'll go back in and install that plugin. That way, next time we have a video like that, I can play it, or if you want, you can play it. So yeah,
we should do that.
Well, should we wrap things up, you think, Mark?
I'm ready to go. I mean, I don't really have anything else to talk about. Just waiting for my 3D printer to arrive, and then we can move on with Alciphon. And I think Jeremiah has a couple experiments, but he couldn't make it. And we'll talk about them next time.
Yeah. Well, no,
by the way, which 3D printer did you order?
It's from Project R3D. It's like a small boutique company that basically of 3D printer enthusiasts who decided to make their own printer that wasn't mass produced yet, and it has a really cool printing bed that uses spring steel that you can just snap, you bend it and it comes right off, and it has a whole bunch of really cool features like super strong aluminum
So
studs.
is it the dataless?
Yeah, the dataless, and we also got their upgraded shroud and stuff that aren't even on the website yet. So that's the printer we got. Supposed to be accurate down to 10 microns.
It looks very nice.
Yeah, we'll give you a review on it in 2 weeks.
Yeah, I'll be interested to see what you think about it.
I've seen some reviews online so far, and they looked pretty promising. And this will be my 4th printer, and every single one since the beginning when I started, I printed on it until it died. So this is my 4th printer, and hopefully it'll live long and prosper.
Yeah, and the price is not bad either, too. So that's the price looks pretty decent. So yeah,
there are some cheap, junky Chinese printers out there, but they don't have the level of accuracy and the nozzle temperatures that I need.
Right. Yeah. So yeah, we make our own 3D printing resins and everything here in my lab. So because we 3D print superconducting material, superconducting devices. So as well as we develop we have new forms of ceramics that we are developing and making for 3D printing, ceramic printers. So
what kind of material, what kind of superconducting material can you 3D print? Nitrogen temps or helium temps?
We have, my colleague and I, we've invented a new form of superconducting material. So it's, how should I say? We actually were the first people to make YBCO nanotubes, as well as nano crackers and nano super crackers, I guess. as well as we're the only group to also discovered how to make YBCO spirals, which we're using, which are nano size, and we're using for new forms of antennas and stuff like that, as well as radiation devices. So
one of the experiments that we're working on is the Podklanov impulse experiment, which uses a bilayer of YCBO with a semiconductor in the middle, where they call it the Josephson junction. Are you familiar with that experiment?
I'm familiar only with what I read in the media. I don't know anything beyond that. So I think one person in the last conference had said something about it, but beyond what I've heard you guys talk about and the media, I don't know anything about it. Not really. So I never really followed that very close.
No. Can you print YCBO in large disks?
We have a new 3D printer coming in next month. So we can probably, I think we can print 24-inch disc. So with our new 3D printer.
Is this pure YCBO or is there resin mixed in with it?
No, it would be a pure YBCO ceramic. So.
Wow. Okay. Yeah, we're definitely gonna have to talk then, because we'd like to get some. I mean, 24 inches is insane. NASA had trouble getting 8 inches. Yeah, if we can get something like that here in the lab, there's a lot of experiments that I want to try.
Yeah, there would have to be a lot of discussion on that with the business part of my company in Singapore. I have a company in Singapore which would regulate how we would proceed on something like that. So that would have to go through the business group. Yeah, so yeah, I have a company, but also a business group which actually handles all of my inventions and technology that we develop in my laboratories.
Why out of Singapore?
Singapore. I would have to get the name card.
No. Why do you select your business group out of Singapore?
Why
Because I'm origin.
Well,
Because I'm
our group is very multinational. Singapore is close to Japan. The tax haven aspect of it is very good.
Right.
And in the US is very, how should we say, unbusiness friendly.
Try California. No, the reason why I ask is I'm originally from Malaysia, and Singapore got its independence from Malaysia. So our families are split between the two countries.
Well, my wife is in KL, and my daughter and son go to what do you call it? You pay for the school. What's that called? I forgot what they call that. International
School.
International school. Yeah, I guess that's what you say. So yeah, so they go to international school in KL now. They were in Penang. School wasn't so good, so we moved them to KL.
Right.
So about 2 months ago, so they started in KL. So yeah, so
Yeah, why don't they study in
I like Malaysia, by the way. So except for the toilets. So
and the politics. The politics is horrible.
well, I never got involved in that. So that's
No, you don't have to get involved. The country is so corrupt, you don't have to get involved.
Yeah.
So why don't your family study in Singapore, not instead of Malaysia?
Well, Singapore at the time, Singapore didn't the timing for the schools weren't good.
Oh.
At the time. And also Singapore is pretty expensive to live in. we did look at it, but I gotta tell you, I think, you look at a one-bedroom apartment in Singapore is equal to a five-bedroom apartment in the US. So, or what you would call a mansion, right? So,
The city is clean and
oh yeah.
very well managed. You pay the same price in California and it's a dump.
Well, there you go.
Depends on where you live in California.
Yeah, actually, I grew up in Yucaipa, Calamasa, where a little bit, and then we moved to Blythe, where my mom was born. Actually, both were very nice. Cool. That's decades ago, but yeah, I understand California's changed a lot since then. So you're
just jump in. I was at the Singapore airport back in the 80s. It's the cleanest airport. Remember, I can never forget it.
Well, I was there 2 years ago, and I was surprised that when I went into the toilet at the Singapore airport,
right,
it was cleaner
Yeah.
than my table at home. The floor was cleaner than my table at home. So,
Well,
amazing.
they got special toilets there too. No, without getting into
You're talking about the European.
Yeah.
Yeah, they are different, aren't they? Yes, we have those in Japan. Somehow the Europeans don't like toilet paper, so that's why those were actually created. So anyway, yeah.
So I'm curious to know if you've been able to fab devices using the yttrium, barium, copper oxide.
Yes, actually, we made now we're in the process of developing a YVCO device that's nano size that can detect X-rays, and we have another one for gamma radiation. So, and they're nano size. They don't require energy input.
They're hard enough to withstand gamma and the
Yeah.
devices. So, like I've done experiments with infrared sensors where you had to do radiation hardening by thinning it, making it really thin, for example. So the capture cross sections large enough that you're not likely to get it sustain any damage.
Our capture cross section is 11 angstroms.
In angstroms. Oh, okay. And then
the device itself is about 10 nanometer in diameter by 100 nanometer long. But the cross section of the device is 11 angstrom. So.
Wow, that's pretty thin.
Pretty thin, yeah.
Yeah. Okay, well, that sounds cool.
So,
I can't wait till. Is it all like unpublic stuff right now? But it's going to come out.
Unpublic. So totally public. So, and yeah, we have quite a few things that we're working on that in basically are pretty amazing things. So,
well, thanks for sharing.
Yeah,
I appreciate it.
So,
how do you 3D print YCBO? I mean, from my research, in order to create a crystalline structure out of it, you have to like maintain a very steady high temperature for quite a while in order to build up a crystal. How would you
have to sinter it, right? And then not only do you have to sinter it, but you get tons of breaks that come out of the mold. I'm not sure if he's here, but
yeah, that's how everybody else does it. So our materials are unique in the sense that we have no recentering. So we can, well, we have, actually, I should say we have done it. We've taken cardboard and paper and spray painted with our YBCO and and basically demonstrate the Meissner effect. So stuff like that. So so we can spray paint our YBCO. We can mold it by 3D printing. We use resin-based 3D printing for that. Well, so we draw it into wire. There's lots of things that we're doing with it. So.
Okay, that's pretty interesting. I didn't know you can make a wire out of a ceramic.
Well, the way we do it, sure you can.
Mm-hmm.
So, but a lot of this stuff, you know, is not public. I have a paper that I published 2 years ago, and I've got 2 more papers coming out in the next few months, but none of it talks about anything that I've told you about. So.
Okay, so we definitely have to connect after the conference about those other things we talked about, and see what we can do. Anyone else? Tim,
Yeah,
I think
yeah, we're all set.
we're all set.
Well, happy Easter to everyone. And if you celebrate another holiday, happy other holiday. So yeah, let's call it a night. Let's call it a night.
Happy Easter. Okay.
Happy Easter.
Happy Easter, guys.
Live long and prosper.
All right.
Have a good one, guys.
Okay.